Over 140 million years ago, long before humans existed, the Earth was very different. The Jurassic Era featured large forests of conifers and extensive ferns, along with swamps inhabited by animals no longer alive today. Dinosaurs lived on continents that were slowly moving apart. Some hunted in groups, while others fed on plants. Oceans contained large marine reptiles and many fish, and pterosaurs flew in the air. Volcanoes were active, mountains were forming, and rivers flowed through the land. Life during this time was diverse, with many different species occupying a variety of environments. Before we begin the video, subscribe to our channel and let us know in the comments below where in the world you're watching from. We're always eager to hear where our viewers are tuning in from. Over 199 million years ago, the world entered a period that scientists today call the Jurassic Era. This was a time that stretched across more than 50 million years, finally coming to an end around 145 million years ago. The Jurassic Era was not simply a stretch of time marked by numbers on a calendar. It was an era of dramatic change, growth, and evolution. A period when the Earth itself seemed to be alive with movement and transformation. The continents, which had been united as the supercontinent Pangaea during the preceding Triassic period, began to slowly drift apart. This gradual shifting of land created new coastlines, new shallow seas, and new connections between habitats. As a result, life began to adapt and flourish in ways that had never been seen before, filling niches across both land and water. During the early part of the Jurassic, roughly around 199 million years ago, the planet was still recovering from the mass extinction event that had ended the Triassic period. Many species that had dominated the late Triassic had disappeared, leaving wide-open ecological spaces. The climate at this time was generally warmer than it is today, with no polar ice caps and higher levels of carbon dioxide in the atmosphere. This warm climate created a world where deserts, forests, and vast coastal wetlands could exist in close proximity. The land masses were slowly splitting, forming long, narrow continents and shallow seas that teemed with life. Inland, rivers carved deep valleys, creating fertile floodplains that would eventually support the growth of some of the largest creatures to ever walk the planet. In the early Jurassic, plant life was already diverse, with forests of conifers, cycads, and ferns stretching across continents. These plants formed dense canopies and thick undergrowth, creating habitats for a wide variety of animals. Gymnosperms, particularly conifers, became dominant in many regions, providing both food and shelter for emerging dinosaur species. The first true mammals were small and nocturnal, scurrying underfoot and avoiding the larger predators that roamed the land. These early mammals were often no larger than modern rats, but they were important because they represented a branch of life that would later evolve into many different forms, including creatures that would ultimately dominate the world long after the Jurassic had ended. By the middle of the Jurassic, around 165 million years ago, the breakup of Pangaea had progressed even further. The continents had begun to resemble the outlines of modern land masses, though still connected in places by narrow land bridges. This separation allowed different species to evolve independently, giving rise to regional diversity. The seas, warmed by the planet's high temperatures, became home to vast numbers of marine reptiles, ammonites, and other invertebrates. Coral reefs flourished in the shallow waters, building complex structures that supported an incredible diversity of life. Sharks and rays swam in abundance, preying on smaller fish and invertebrates, while giant predators such as plesiosaurs and ichthyosaurs dominated deeper waters. The Jurassic Era is particularly famous for the age of dinosaurs, which saw the rise of some of the most iconic species in the fossil record. By the Middle Jurassic, large herbivorous dinosaurs such as sauropods were roaming the land. These massive creatures, including relatives of Brachiosaurus and Diplodocus, had long necks that allowed them to reach the tops of trees and enormous bodies that required vast amounts of food. Their sheer size provided protection from predators, though giant carnivorous dinosaurs, including early relatives of Allosaurus, were formidable hunters that kept herbivore populations in check. Dinosaurs were not only numerous but also varied in shape, size, and behavior, occupying nearly every ecological niche. Some were fast and agile, able to chase down prey or flee from danger, while others moved slowly but had powerful defenses like thick armor or long tails. Around 150 million years ago in the late Jurassic, the continents were continuing to drift apart, creating new ocean basins and altering climate patterns. These changes influenced the evolution and migration of species. Dinosaurs and other land animals began to spread into new regions, adapting to local environments. In North America, large sauropods and theropods roamed the floodplains and forests, while in Europe, smaller ornithischians thrived in woodlands and along riverbanks. The oceans were dominated by giant marine reptiles, including pliosaurs with massive jaws and long-snouted ichthyosaurs capable of high-speed hunting. Flying reptiles known as pterosaurs filled the skies, with wingspans reaching up to 10 meters in some species, while insects of all shapes and sizes explored every layer of the terrestrial world. During this period, the Earth's climate remained generally warm, but there were variations. Some regions experienced seasonal rainfall, while others had arid conditions. These differences in climate, combined with the splitting continents and rising mountains, created isolated environments where species could evolve independently. Such isolation was crucial for the diversification of life. In these separate habitats, unique species emerged, some of which were precursors to future forms, while others would vanish entirely by the end of the Jurassic. The diversity of life was matched by the complexity of ecosystems, which included intricate food chains and interactions among predators, prey, plants, and smaller organisms. Fossil evidence shows that by the late Jurassic, forests of conifers and cycads were widespread, covering much of the land. These forests were home to countless herbivorous dinosaurs that grazed on leaves, ferns, and low-lying plants. Predators such as allosaurids and ceratosaurs patrolled these forests, hunting in packs or stalking prey individually. Along rivers and lakes, freshwater fish and amphibians thrived, while the first crocodile-like reptiles moved between water and land. The skies were filled with pterosaurs, ranging from small, bird-sized species to massive giants that could glide for long distances over oceans and inland valleys. The interactions between these species created complex ecosystems that were both fragile and dynamic, capable of being altered by climate changes, volcanic eruptions, and sea level fluctuations. Throughout the Jurassic Era, volcanic activity was common in many regions. Lava flows and ash deposits reshaped the landscape, creating new soils and altering river paths. Volcanoes also affected climate by releasing gases into the atmosphere, which could warm the planet or change rainfall patterns. The movement of tectonic plates caused earthquakes, uplifted mountains, and opened new ocean basins, all of which influenced the distribution and evolution of species. These geological processes were slow on a human timescale, but profound over millions of years, leaving lasting marks on the planet's surface and providing the framework for ecosystems to develop. By the very end of the Jurassic, around 145 million years ago, the Earth had been transformed dramatically since the beginning of the period. The continents were continuing to move toward their modern positions, and the oceans were filled with life, including early forms of many groups that would dominate the Cretaceous period. Dinosaurs remained the dominant land animals, with an increasing number of specialized forms adapted to different diets and environments. Mammals, though still small and often nocturnal, were diversifying slowly, experimenting with new ways of living. Insects and plants continued to co-evolve, with flowering plants still yet to appear but with ferns, cycads and conifers spreading widely. The oceans, rivers and lakes remained rich with fish, amphibians and reptiles, creating a balanced yet ever-changing web of life. The Jurassic Era, spanning from 199 million to 145 million years ago, was a period of immense transformation. The slow but continuous movement of continents reshaped the land, creating new habitats and isolation that promoted evolution. Warm climates, extensive forests, and shallow seas provided the foundation for some of the most remarkable life forms in Earth's history. Dinosaurs became dominant, marine reptiles thrived, and early mammals and insects explored niches that would influence the future of life on the planet. Throughout the entire period, the planet itself was alive with activity. Tectonic shifts, volcanic eruptions, changing climates, and evolving ecosystems all combined to create a dynamic and endlessly fascinating world. The sheer length of the Jurassic Era, over 50 million years, allowed for gradual but profound changes. Species could adapt to shifting environments, migrate across newly formed land bridges, or become isolated and evolve into new forms. Fossils from this period, found across all continents, provide a detailed record of these changes, revealing the rise of enormous sauropods, fierce predators, and thriving marine ecosystems. The Jurassic Era set the stage for the Cretaceous period, during which even more dramatic evolutionary changes would occur, but the groundwork for these transformations had already been laid during this remarkable stretch of geological time. Life during the Jurassic Era was never static. Rivers carved new valleys, rainfall patterns shifted and sea levels fluctuated, each change opening new opportunities for plants and animals. The evolutionary pressures imposed by these changes encouraged specialization, resulting in species that were highly adapted to particular environments. Forests could suddenly dry out or flood, forcing animals to migrate or adapt, while volcanic eruptions could wipe out local populations, giving survivors the chance to expand. In the oceans, marine reptiles competed for prey, while ammonites and other mollusks diversified, their shells forming complex patterns that fossilized over millions of years. The interplay between geological processes and biological evolution was constant. Mountains rose and eroded, creating mineral-rich soils that supported forests and herbivores. Shallow seas expanded and contracted, altering the habitats of marine organisms. Climate shifts, although gradual, created pressures that drove adaptation and speciation. Over the course of 54 million years, life on Earth grew more complex, ecosystems became more interdependent, and the planet's surface was molded into a form that would begin to resemble the Earth we know today. Every fossil discovered from the Jurassic Era tells a story of survival, adaptation, and change. The long-necked sauropods remind us of the scale of life on land, while the predatory theropods illustrate the relentless struggle for survival. The marine fossils reveal ecosystems teeming with life, from tiny plankton to massive reptiles patrolling the open waters. Even small creatures like early mammals and insects demonstrate how life could persist and diversify in the shadow of giants. Over 54 million years, these interactions and adaptations created a rich tapestry of life, demonstrating the resilience and inventiveness of living organisms under the pressures of a changing planet. From 199 million to 145 million years ago, the Jurassic Era was a time of dynamic geological and biological activity. The slow breakup of Pangaea, the warm climate, and the flourishing of plants and animals combined to create an Earth filled with diversity and complexity. Every river, lake, forest, and coastline was home to species uniquely adapted to its conditions, and every volcanic eruption or tectonic shift altered the opportunities and challenges faced by life. In this way, the Jurassic Era can be seen not merely as a block of time, but as a period of continuous change and evolution, where the stage was set for the future of life on Earth, including the rise of even more spectacular creatures in the periods that followed. The richness of the Jurassic Era can also be understood through its contribution to the fossil record. Fossils from this time, including footprints, bones, and plant imprints, reveal not just the presence of life, but the interactions and behaviors of species. Tracks show the movement of herds, the hunting strategies of predators, and the migration routes of various animals. Fossilized plants reveal forest structures, the diversity of vegetation, and the diets of herbivorous species. Marine fossils display predator-prey relationships, reproductive strategies, and even social behavior in some species. Each discovery adds depth to our understanding of life between 199 million and 145 million years ago. Even as the Jurassic Era progressed, life experimented in remarkable ways. Some dinosaurs evolved complex social behaviors, traveling in herds or possibly developing forms of communication. Pterosaurs adapted to specialized flight patterns, exploiting both inland and coastal niches. Mammals remained small but diverse, exploring new dietary strategies and nocturnal niches to avoid larger predators. Insects evolved alongside plants, pollinating gymnosperms and helping shape the structure of forests. Marine ecosystems continued to expand in complexity, with cephalopods, fish, and reptiles interacting in intricate food webs. The geological and biological changes of the Jurassic Era were intertwined. The rise of mountain ranges altered wind and rainfall patterns, shaping forests and deserts. The opening of new seaways allowed marine species to disperse and colonize new regions. The slow movement of continents created barriers that isolated populations, driving speciation and regional adaptation. Over millions of years, these processes led to a proliferation of species and ecosystems that were rich in variety and complexity. the legacy of these changes can still be traced in the fossil record and in the patterns of biodiversity we observe in the world today. The Jurassic Era was defined not only by its extraordinary animals and plants, but also by the ongoing transformation of the Earth itself. The slow drift of continents, the rise and fall of sea levels, and the continual shaping of landscapes through erosion and volcanism created a dynamic and ever-changing planet. Species were constantly challenged to adapt, migrate, or face extinction. The interplay of life and geology produced a world that was at once stable enough to support complex ecosystems and flexible enough to allow evolutionary experimentation. Over more than 50 million years, the Jurassic Era became one of the most fascinating chapters in Earth's history, a time when life expanded, ecosystems matured, and the stage was set for the dramatic changes that would come in the Cretaceous period. The end of the Jurassic Era, around 145 million years ago, marked the close of this remarkable time of transformation. The continents had moved closer to positions recognizable today, oceans had reshaped coastlines, and ecosystems were rich and varied. Dinosaurs continued to dominate land environments, marine reptiles ruled the seas, and the first flowering plants were still yet to emerge. Mammals continued their slow diversification, insects proliferated, and the interplay between land, sea, and sky created complex, interdependent ecosystems. This long stretch of 54 million years had seen the rise of iconic species, the formation of continents, and the flourishing of life in ways that would echo far into the future. The Jurassic Era remains one of the most studied and fascinating periods in Earth's history. Fossils, sediment layers, and geological formations provide a window into a world that existed from 199 million to 145 million years ago, revealing the ongoing evolution of life, the shifting of continents, and the changes in climate and ecosystems. This period, stretching over more than 50 million years, captures a chapter in which the Earth was in motion, both literally and figuratively, as life continued to diversify and adapt under the pressures and opportunities created by a planet in constant transformation. The extraordinary span of the Jurassic Era, from 199 million to 145 million years ago, offers endless insights into the processes that shape our planet. It was a time of incredible diversity, of massive and tiny creatures, of forests and oceans teeming with life, and of continents in motion. Each fossil, rock layer, and geological formation from this time provides clues about the ancient world, offering glimpses of ecosystems, climates, and species interactions. The changes that occurred during the Jurassic Era laid the foundation for the Cretaceous period and ultimately for the world as we know it today. In summary, the Jurassic Era was a period of more than 50 million years, beginning around 199 million years ago and ending around 145 million years ago. It was characterized by continental drift, warm climates, rich and diverse ecosystems, the rise and dominance of dinosaurs, the proliferation of marine life, the evolution of early mammals, and the ongoing reshaping of landscapes by rivers, volcanoes, and tectonic activity. Life on Earth during this time was dynamic and ever-changing, responding to the shifting environment and evolving in ways that would have lasting impacts on the planet's biological and geological history. The span of time from 199 million to 145 million years ago stands as one of the most remarkable chapters in the Earth's history, a period of continual evolution, adaptation, and environmental change. Life flourished in diverse habitats, from dense forests to vast inland seas, and from river valleys to open plains. Dinosaurs, marine reptiles, and early mammals evolved, adapted, and interacted, creating complex ecosystems that reflected the dynamic nature of the planet. The Jurassic Era remains a testament to the resilience of life and the ongoing transformation of Earth over millions of years, a world in motion that shaped the course of evolution for all time. The end of the Jurassic Era, around 145 million years ago, marked a transition, setting the stage for the even more dramatic changes of the Cretaceous period. The patterns established during this time, from continental drift to climate fluctuations, from the rise of new species to the extinction of others, created the foundation for future evolution. The fossil record preserves this story in detail, showing how life responded to the challenges and opportunities of the time. Every layer of rock, every preserved bone, every trace fossil contributes to our understanding of a world that existed for over 50 million years, a world of movement, growth, and endless adaptation. By the end of the Jurassic Era, the Earth had already been profoundly shaped by 54 million years of geological and biological activity. The continents were drifting toward positions that would eventually form modern oceans and land masses. Ecosystems had grown rich and complex, and life had explored a variety of forms and strategies. From massive sauropods to small mammals, from coral reefs to dense forests, the diversity of life was astounding. The interplay of climate, tectonics, and evolution during this period created a living, changing world that set the stage for the next chapter in Earth's history, while leaving a legacy that continues to fascinate scientists and enthusiasts alike. The Jurassic Era, extending from 199 million to 145 million years ago, represents a long and transformative period in the Earth's history. It was a time of movement, adaptation, and flourishing life, where continents drifted, seas expanded, forests grew, and animals evolved into forms both gigantic and tiny. Every aspect of the planet, from its surface to its climate to its living organisms, was involved in an intricate dance of change. Fossils from this era provide a window into a world that existed over 50 million years ago, revealing the remarkable complexity of life and the power of natural forces to shape it. This era, covering over 50 million years, was marked by the rise of iconic dinosaurs, the dominance of marine reptiles, the slow evolution of mammals, the proliferation of forests and plants, and the ongoing reshaping of the Earth through tectonic activity, volcanic eruptions, and climatic fluctuations. It was a period when life not only survived but also thrived, filling ecosystems with complexity and diversity. Every new discovery, from a bone to a fossilized footprint, adds to our understanding of how life evolved during this remarkable time from 199 million to 145 million years ago, painting a detailed picture of the Jurassic Era as a period of endless adaptation, change, and thriving life across the planet. Over 200 million years ago, the Earth was a very different place than it is today. The continents were not in the positions that we are familiar with now, and the shapes and sizes of the land masses were dramatically distinct. Most of the land on the planet was joined together in a single enormous supercontinent known as Pangaea. This massive landmass stretched from the polar regions near what we now call the North and South Poles down to equatorial areas, forming a giant continuous expanse of land. It was roughly shaped like a giant sea or a crescent, curving around the edges of a vast ocean called Panthalassa. This ocean covered almost the entire rest of the planet, acting as a massive global body of water that stretched from pole to pole, and it was incredibly deep and largely empty, with only a few smaller seas and shallow regions near the edges of Pangaea. The central part of Pangaea was dry and often arid, with extreme temperatures in summer and winter, while the coastal regions and margins near shallow seas had a more moderate climate, influenced by the nearby water. As the supercontinent began to slowly move and drift due to the process of plate tectonics, the Earth's surface began to change in dramatic ways. Land masses shifted away from one another over millions of years, stretching, colliding, and breaking apart. When Pangaea split, it gradually formed the continents that we recognize today. But during this ancient period, these continental pieces were in very different positions, which had a profound effect on the climate, ocean currents, and the life forms that could live there. The arrangement of mountains, valleys, and shallow seas created natural pathways and barriers for animals and plants. Large mountain ranges rose from the collisions of tectonic plates, creating highlands that affected weather patterns, rainfall, and river systems. Mountains also acted as barriers that separated ecosystems, leading to different species evolving on either side in isolation. Some of these mountain ranges stretched for thousands of kilometers, towering above the land and often covered with thick forests, ferns, and conifers. In certain areas, volcanic activity contributed to the formation of new mountains, plateaus, and fertile valleys, while lava flows and ash deposits changed the landscape over long periods of time. The shallow seas, known as Epicontinental or inland seas, were extremely important in shaping life on Earth. These seas were not very deep compared to the vast oceans, often only a few hundred meters in depth, and they extended across wide parts of the continents, flooding lowlands and forming extensive coastlines. These shallow waters were rich in nutrients and sunlight, making them ideal habitats for a wide variety of marine organisms. Tiny plankton, algae, and other microscopic life flourished in these shallow seas, forming the base of food chains that supported larger animals such as fish, marine reptiles, and shellfish. Coral reefs began to appear in some regions, creating complex underwater landscapes that provided shelter and breeding grounds for countless species. These seas shifted over time as the continents moved, sometimes expanding to cover large portions of the land, and at other times receding, leaving behind extensive salt flats, lagoons, and river deltas. The movement of water between the seas and the oceans also helped regulate temperatures and allowed species to spread from one area to another, though barriers like mountain ranges and isolated landmasses still caused unique species to evolve independently. The coastlines during this period were constantly changing due to the rise and fall of sea levels. Even small variations in sea level could flood vast areas of flat continental land, creating new shallow seas, bays, and estuaries. These coastal areas were particularly productive and diverse, providing abundant food and shelter for animals that lived both in the water and along the shore. Marine reptiles such as ichthyosaurs, plesiosaurs, and plesiosaurs patrolled the shallow waters near the coasts, hunting fish and smaller marine animals. Shelled creatures like ammonites and belemnites thrived in these regions, often leaving behind extensive fossil records that we can study today. Shorelines were often lined with mangrove-like vegetation, ferns, and early conifers, providing additional habitats for small reptiles, amphibians, and insects. Rivers and streams flowing from the mountains into these shallow seas carried sediments, minerals, and nutrients, creating fertile deltas and mudflats that supported a wide array of life. The flow of these rivers also connected different shallow seas, allowing species to migrate and adapt to new environments over time. The positions of land masses and oceans also shaped the climate and weather patterns of the period. Large continents far from the equator experienced extreme seasonal changes, with harsh winters and hot summers, while smaller coastal regions near the equator enjoyed warmer, more stable conditions. Mountains forced air to rise, causing rainfall on one side while creating dry conditions on the other, producing deserts and arid regions in the rain shadows. Shallow seas moderated local climates by absorbing heat during warm seasons and releasing it during cooler seasons, creating stable environments that allowed diverse ecosystems to flourish. The combination of vast deserts, fertile plains, dense forests, and shallow seas created a patchwork of habitats across the continents, each with its own set of plants and animals adapted to the specific conditions. This diversity of landscapes contributed to the rapid evolution of species, as animals and plants adapted to the wide variety of environmental pressures presented by the shifting continents and changing seas. Mountain ranges during this period were not only barriers but also centres of biodiversity. Valleys and highlands provided refuge for species escaping the heat or aridity of the lowlands. Forests on mountain slopes were home to enormous ferns, cycads, and towering conifers, while open plains and plateaus supported grazing dinosaurs, small mammals, and other creatures adapted to life on flat, dry land. Mountains also influenced the flow of rivers, which carved deep valleys and created natural routes for migration. Rivers originating from highlands often ended in shallow seas or coastal plains, transporting nutrients and sediments that enriched the soil and supported lush vegetation along their banks. Floodplains, marshes, and wetlands formed where rivers slowed down near the coast, creating additional habitats for aquatic and semi-aquatic life. These freshwater systems connected inland regions with the oceans, allowing species to disperse over large areas while also providing corridors for evolution and adaptation. The arrangement of continents also affected ocean currents, which in turn influenced global climate patterns. As the continents shifted apart, narrow ocean passages formed, altering the flow of warm and cold water around the planet. These currents distributed heat from the equator to higher latitudes, affecting air temperatures, rainfall, and the spread of species. Shallow seas along continental margins acted as reservoirs for warm water, supporting coral reefs, fish populations, and early marine reptiles. Meanwhile, deep oceans transported cooler water from polar regions, creating upwelling zones rich in nutrients that fueled plankton blooms and supported larger marine predators. The interplay between continental positions, mountains, shallow seas, and ocean currents produced a dynamic system in which life had to constantly adapt to changing conditions. Species that thrived in one region might struggle or disappear entirely in another if the seas advanced. Mountains rose, or climate patterns shifted. In the interior of the continents, far from the moderating influence of the shallow seas, life faced additional challenges. Large deserts and arid plains emerged where rain was scarce, while intermittent rivers and lakes provided crucial sources of water. Animals and plants adapted to these harsh environments often developed special strategies to conserve water, find food, or escape predators. Some species migrated seasonally, following rivers and oases, while others evolved to survive long periods without direct access to water. These inland areas were often less stable than coastal regions, as small changes in rainfall, river flow, or temperature could dramatically alter habitats. Shallow seas that occasionally flooded lowlands transformed these areas into temporary wetlands, allowing certain species to take advantage of the abundance of resources before returning to the drier land. The configuration of continents also influenced evolutionary pathways by creating isolation for certain species. As mountains rose, seas receded, or land bridges formed, populations of animals and plants became separated from one another. Over time, these isolated populations evolved distinct characteristics, giving rise to new species adapted to specific environmental conditions. Some dinosaurs developed long necks to reach high vegetation, others grew massive bodies to deter predators, and some evolved advanced hunting strategies or social behaviors to survive in their unique habitats. Similarly, marine life in shallow seas adapted to local conditions, with different species of fish, mollusks, and marine reptiles dominating in different regions. Coral reefs, sandbanks, and underwater ridges acted as natural laboratories, encouraging the diversification of life by providing opportunities for specialization and adaptation. The shifting positions of continents also affected volcanic activity, which in turn shaped the geography and life on Earth. When tectonic plates collided, mountains rose, and volcanic eruptions released lava, ash, and gases into the atmosphere. Lava flows could create new land or cover existing habitats, while ash clouds sometimes blocked sunlight, affecting temperatures and plant growth over large areas. Volcanic soils, however, were often rich in minerals and nutrients, supporting lush vegetation that attracted herbivorous dinosaurs and other land animals. Volcanic islands occasionally emerged in shallow seas, providing new environments for species to colonize and adapt. These islands often became isolated ecosystems where unique forms of life could evolve without interference from mainland species. The interaction between tectonics, volcanoes, mountains, and shallow seas produced a constantly changing planet, where life had to be resilient and adaptable to survive. Over millions of years, the combination of continental movement, mountain formation, shallow seas, and changing climates created a complex web of habitats that supported a remarkable diversity of life. Inland deserts and river valleys, coastal plains and deltas, high mountain slopes and deep valleys, shallow epicontinental seas and expansive oceans all provided unique niches for plants, animals, and marine organisms. The interactions between land and water, heat and rainfall, mountains and plains, shallow seas and deep oceans shaped not only the geography of the planet but also the evolutionary paths of countless species. Life was constantly responding to the opportunities and challenges presented by this intricate arrangement of land, water, and climate, producing an astonishing variety of forms and behaviors that laid the foundation for future ecosystems. The positions of continents, the height and extent of mountain ranges, and the spread of shallow seas were not just physical features of the Earth. They were the forces that guided the story of life, influencing where species could live, how they could survive, and how they would change over time. Even small changes in geography could have large effects on ecosystems. A rise in sea level could transform a desert into a shallow sea, while the uplift of mountains could redirect rivers, alter rainfall patterns, and create new habitats for plants and animals. As continents drifted apart, isolated landmasses developed unique species, some of which had no counterparts elsewhere. Similarly, shallow seas that expanded across continental interiors became centers of marine biodiversity, supporting complex food chains and nurturing evolutionary experiments that could last for millions of years. These interconnected systems of land, water, and life were dynamic and ever-changing, constantly reshaping the Earth's surface and the creatures that inhabited it. Mountains, rivers, inland seas, and coastlines acted as both barriers and bridges, creating challenges for survival, while also opening new possibilities for exploration and adaptation. The geography of the planet during this period was crucial in determining patterns of migration and dispersal. Animals and plants followed rivers, coastlines, and shallow seas to spread into new areas, while mountain ranges and deserts prevented movement, keeping populations separated and encouraging the development of distinct species. Sea levels fluctuated over time, sometimes exposing land bridges that connected previously isolated continents or islands, allowing species to move into new territories. Shallow seas served as corridors for marine life, while deep oceans limited the range of certain species, confining them to specific habitats. The interaction between geography and life created a delicate balance in which both the physical environment and living organisms shaped each other over millions of years. Large mountain ranges influenced not only climate and migration, but also the course of rivers and the formation of lakes and inland seas. Water flowing down from mountains carved valleys and canyons, while depressions in the land filled with water, creating lakes that became important sources of life. These freshwater bodies provided habitats for amphibians, fish and insects, while also attracting terrestrial animals that relied on water for drinking and food. Over time, the accumulation of sediments in lakes and rivers created fertile floodplains that supported dense vegetation and herbivorous dinosaurs. The interaction between landforms and water systems created diverse and productive ecosystems, with life adapting to the opportunities provided by each geographic feature. Mountains, plains, rivers, lakes, and shallow seas all combined to create a world of extraordinary complexity and richness, where every change in the land or water could ripple through ecosystems and influence the course of evolution. This pattern of interconnected landmasses, mountain ranges, shallow seas, and dynamic climates persisted over tens of millions of years. As continents continued to drift, mountains slowly eroded, rivers carved new valleys, and seas advanced or retreated across the land. Each shift in geography produced new challenges and opportunities for life, shaping the development of species, communities, and ecosystems. Marine life in shallow seas adapted to changing water levels and temperatures, while terrestrial life evolved strategies to survive in mountains, plains, and deserts. The interplay between the positions of continents, the heights of mountains, and the extent of shallow seas created a constantly evolving stage upon which the story of life unfolded, with every landform and body of water contributing to the complex and fascinating patterns of biodiversity. The distribution of continents and oceans also affected the planet's atmosphere and weather systems. Large continents could create temperature extremes, while shallow seas helped stabilize coastal climates. Mountains forced air currents to rise, producing rainfall on one side and dry conditions on the other, shaping the distribution of deserts and forests. The position of oceans and seas influenced the movement of warm and cold currents, affecting global temperatures and precipitation patterns. These combined effects of geography, water, and climate determined the success of species in different regions, influencing where they could live, how they could reproduce, and how they would evolve. Mountains and shallow seas, deserts and rivers, coasts and plains, all of these elements work together to form a dynamic and interconnected system, constantly shaping the planet and the life it supported. The constant shifting of continents, the rise of mountains, and the spread of shallow seas also affected the formation of sedimentary rocks, which preserved evidence of life for millions of years. Rivers carried sediments into shallow seas, creating layers of mud, sand, and organic material that eventually hardened into rock. These rocks often contained fossils of plants and animals, providing valuable records of the ecosystems that existed during different periods. Mountains eroded over time, supplying minerals and sediments to rivers and seas, while volcanic activity added layers of ash and lava to the geological record. The interplay of land, water, and life not only shaped the present, but also left a detailed record of the past, capturing the positions of continents, the extent of mountains, and the richness of shallow seas for future generations to study. Shallow seas were particularly important in this geological record. Their sediments often contained abundant fossils, preserving details of marine life that thrived in these sunlit waters. Coral reefs, mollusks, fish, and marine reptiles left behind shells, bones, and imprints that provide clues about ancient ecosystems. Inland seas occasionally connected with rivers, allowing species to move between freshwater and marine environments. Coastal plains and deltas accumulated sediments from both land and sea, creating rich layers of rock that document the changing geography over millions of years. Mountains and valleys contributed to this record by supplying sediments and shaping the flow of rivers, while volcanic eruptions occasionally buried habitats, preserving entire ecosystems in ash. The Earth's continental geography, with its dynamic mountains, shallow seas, and shifting land masses, created an environment in which life could diversify, adapt, and evolve. The position of continents dictated the flow of oceans and rivers, the formation of deserts and forests, and the development of unique ecosystems. Mountains influenced climate and migration, while shallow seas provided rich habitats for marine life. Rivers and lakes connected inland regions to the coast, allowing species to disperse and adapt to new environments. Every mountain, valley, and shallow sea acted as a factor in shaping life, with each geographic feature contributing to the complex web of ecosystems that covered the planet. The interaction between the positions of continents, the height and spread of mountains, and the presence of shallow seas created a living mosaic of landscapes, waterscapes, and ecosystems, continuously changing over millions of years. Life responded to these changes in remarkable ways. Species evolved to exploit the niches provided by mountains, plains, rivers, lakes, and shallow seas. Herbivores adapted to feed on specific plants, predators evolved strategies to hunt in particular terrains, and marine life developed forms suited to shallow or deep waters. The arrangement of continents determined migration routes, isolated populations, and areas of high biodiversity. Shallow seas acted as cradles of life, while mountains and deserts created challenges that required adaptation and resilience. The Earth's geography, with its ever-changing mountains, rivers, lakes, coasts, and seas, guided the course of evolution and created the intricate patterns of life that we continue to study and marvel at today. The interplay between mountains, shallow seas, and continental positions also influenced the long-term stability of ecosystems. River deltas and coastal plains often became centers of high productivity, supporting dense populations of plants and animals. Inland deserts and arid plains created selective pressures that shaped the physiology and behavior of species. Mountains and highlands served as refuges during climatic extremes, while shallow seas provided corridors for marine life to expand and diversify. The constant movement of continents and shifting of seas meant that habitats were rarely static, forcing species to continually adapt or migrate. Over millions of years, these processes resulted in the creation of complex food webs, diverse ecosystems, and a rich tapestry of life across the planet, with every geographic feature playing a role in shaping the course of evolution. The positions of continents, the rise of mountain ranges, and the extent of shallow seas were not only physical features but also powerful forces that shaped life on Earth. Mountains directed rivers and rainfall, influenced climate, and created barriers and corridors for species. Shallow seas provided nutrient-rich habitats that supported abundant marine life and facilitated dispersal between regions. The drift of continents opened new oceans and closed old seas, reshaping the planet's surface and affecting ecosystems. Each change in geography influenced evolution, biodiversity, and the distribution of life, producing the dynamic, ever-changing world that characterized this ancient period. Mountains, valleys, shallow seas, rivers, and coasts all work together to create a living planet in which the positions of land and water dictated the possibilities for survival, adaptation, and growth. Even the smallest features of the landscape had effects that rippled across ecosystems. River bends created microhabitats for fish and amphibians, shallow lagoons served as nurseries for marine species, and mountain foothills provided shelter for small mammals and reptiles. The interactions between these features and the larger geography of continents and shallow seas created a hierarchy of habitats, from vast oceans and epicontinental seas to inland lakes, rivers, and valleys. Life adapted to each level, with species evolving to exploit the resources and conditions available in every niche. The Earth's continental geography was thus a living system, continuously reshaping itself and the life it supported, with mountains, shallow seas, rivers, and land masses acting as both sculptors and stages for the drama of evolution. Shallow seas in particular played a central role in connecting different regions. They served as highways for marine species, linking coastal ecosystems with inland seas and allowing for the spread of biodiversity. Islands and shallow banks within these seas became isolated environments where species could evolve independently. Periodic changes in sea level created temporary land bridges or separated populations, encouraging diversification. The climate during the time period under discussion was generally warm and humid, with a few brief periods of dryness, and this warmth stretched across most of the planet. During this era, the Earth's atmosphere held more carbon dioxide than it does today, which caused the planet to maintain higher average temperatures year-round. The oceans were warmer, the poles were not covered in ice like they are in the modern world, and tropical conditions extended much further from the equator than we see in the present day. Land masses that now occupy temperate regions experience subtropical or even tropical conditions. This high global temperature meant that plant life could grow almost everywhere, and forests thrived even in areas that are now very cold or dry. Ferns, cycads, and conifer trees dominated the landscapes, and they adapted well to the moist and warm environment. Rainfall was plentiful in most regions, although some areas experienced seasonal dryness, creating a variety of local climates that influenced where animals and plants could live. Humidity was a defining feature of the climate, and it had a strong influence on both the land and the oceans. Moisture in the air was high because of the warm temperatures and the abundant surface water from lakes, rivers, and seas. This moisture fueled intense storms and frequent rainfall in some regions, supporting lush forests that could reach impressive heights and grow very densely. In many places, the ground was often soft and marshy due to the constant presence of water, forming wetlands, swamps, and boggy areas that would become prime habitats for various creatures. Tropical storms and cyclones, though not identical to those of the modern world, were likely frequent in coastal regions, with strong winds and heavy rainfalls reshaping the landscapes and spreading sediments that created fertile soil. Rivers and streams often overflowed their banks during the rainy season, creating floodplains that supported a rich diversity of plant and animal life. The frequent rains and warm temperatures encouraged rapid growth of vegetation, which in turn provided abundant food and shelter for the animals of the time. Even though the climate was predominantly warm and wet, there were periods when dry seasons occurred. These drier periods were usually seasonal, meaning that certain regions experienced months with little rainfall while others remained moist. In areas that received less water during these dry months, rivers and lakes would shrink, water sources became scarce, and animals had to adapt by migrating or developing ways to conserve water. The dry periods were not uniform across the planet. Some regions that were near the equator may have experienced almost constant rainfall, while regions further from the equator could undergo prolonged dry seasons lasting several months at a time. These seasonal changes created a rhythm in the natural world, dictating patterns of growth, reproduction, and movement for both plants and animals. For plants, adaptations such as deep roots and thick leaves helped survive the periods of dryness, while animals may have moved between wet and dry areas to find food and water. Temperature differences between the equator and the poles were smaller than today, but they still existed. The equatorial regions were extremely warm, supporting dense tropical forests and large rivers, while higher latitudes were cooler, yet still much warmer than modern temperate zones. Because the poles lacked permanent ice caps, sea levels were higher, and shallow seas spread across areas that are now dry land. These warm shallow seas helped moderate temperatures and kept the atmosphere humid, creating a relatively stable climate across wide regions. Polar regions were not frozen deserts. Instead, they could support forests of conifers and other plants capable of surviving the slightly cooler temperatures. The distribution of plant life across different latitudes shows that the warmth of this period allowed ecosystems to exist far beyond the range that is possible in today's cooler world. Wind patterns were influenced by the configuration of the continents and oceans. The supercontinent at the time was large and slowly breaking apart, and the positioning of land masses affected how air circulated around the globe. Winds would carry moisture from the warm seas to inland areas, bringing rain and maintaining humidity far from the coasts. These winds also drove ocean currents that spread heat and nutrients around the oceans, influencing both marine and terrestrial life. Monsoon-like patterns may have developed in some areas, with seasonal winds bringing heavy rains followed by drier periods. The movement of the continents and the formation of mountains and valleys altered local climates, creating rain shadows in some areas where mountains blocked moisture and deserts formed behind them. In other areas, lowlands and coastal plains experienced constant humidity and rainfall, leading to extensive forests and swamps. The atmospheric composition played a critical role in shaping the climate. Higher levels of carbon dioxide compared with today caused a strong greenhouse effect, trapping heat in the lower atmosphere. Oxygen levels were also slightly higher than today, which helped support large animal life, including the enormous reptiles that dominated terrestrial ecosystems. The combination of warm temperatures, abundant moisture, and elevated oxygen created an environment where plants grew quickly, animals could reach massive sizes, and biodiversity flourished. Periodic volcanic activity added carbon dioxide and other gases to the atmosphere, temporarily altering local climates and sometimes triggering short periods of drier or hotter conditions. These volcanic events could lead to temporary warming, increased rainfall, or localized droughts, depending on the scale and location of eruptions. Seasons existed, but they were not as pronounced as in modern temperate regions. Because of the high temperatures and the spread of tropical conditions across large parts of the continents, seasonal variation in temperature was small in most areas. Instead, seasons were defined more by rainfall patterns than by temperature changes. In the wet season, storms were frequent, rivers swelled, and plant growth was at its peak. In the dry season, water became less available, and animals may have concentrated near rivers, lakes, or coastal areas. These seasonal shifts created cycles that influenced reproduction and migration. Many plants may have timed their growth and seed dispersal to coincide with the rains, while animals adapted to move between different habitats to survive the dry periods. The climate also influenced the soils and landscapes of the time. The combination of heat and moisture led to rapid weathering of rocks, producing fertile soils in many regions. These soils supported dense vegetation and allowed forests to spread widely. In some areas, repeated flooding deposited layers of silt and clay, forming river plains and coastal wetlands. Swamps and marshes were common, especially near rivers and in lowlands, and they were home to a diverse array of life. The humid conditions and frequent rainfall prevented large desert areas from forming, although some drier regions may have existed in the rain shadows of mountains or in more inland locations. Oceans and seas were affected by the climate as well. Warm surface waters increased evaporation, adding more moisture to the atmosphere and fueling further rainfall. Shallow seas teemed with life, with coral reefs, shellfish, and various marine reptiles thriving in the warm, nutrient-rich waters. Ocean currents, powered by winds and temperature differences, distributed heat and nutrients across large distances, allowing marine ecosystems to flourish far from the equator. Coastal areas experienced frequent storms and occasional floods, which reshaped coastlines, spread sediments, and created new habitats for plants and animals. Rainfall patterns varied across the globe, influenced by topography and proximity to oceans. Coastal regions generally received heavy rainfall throughout the year, supporting dense mangrove-like forests and marshes. Inland areas experienced more variation, with some regions receiving consistent moisture, while others had distinct wet and dry seasons. Mountain ranges created rain shadows, where moisture from prevailing winds was blocked, leading to semi-arid conditions behind the mountains. Rivers, lakes, and inland seas provided crucial water sources in these drier regions, allowing life to survive even when rainfall was scarce. Humidity not only supported plant life but also had a direct effect on animals. Amphibians thrived in moist environments, reptiles could grow large due to the abundance of food, and insects and other invertebrates found conditions ideal for reproduction and survival. Many animals were adapted to take advantage of the humid climate, with skin, scales, or shells that allowed them to conserve water or withstand wet conditions. The combination of warm temperatures and high humidity created conditions that promoted high biodiversity, with many species coexisting in complex ecosystems. Storms and extreme weather events, although less frequent than in the modern world, were still significant. Seasonal storms could bring heavy rains that flooded rivers and reshaped the land. Coastal storms, including protocyclones, affected shorelines, eroding cliffs, depositing sediments, and occasionally causing the extinction of local populations. Volcanic eruptions added unpredictability to the climate, temporarily changing temperature and rainfall patterns over large regions. Despite these occasional disturbances, the overall climate remained warm, humid, and conducive to life, allowing ecosystems to recover and thrive. Wind patterns, rainfall, and temperature all work together to create diverse habitats. In lowlands and river valleys, lush forests and swamps were common. In upland areas, forests were less dense but still supported diverse plant and animal life. Coastal plains often experienced intense storms, but these storms also spread nutrients and allowed new habitats to form. Inland, rivers and lakes acted as lifelines during dry seasons, concentrating animals and promoting interactions between species. The climate had long-term effects on evolution and the distribution of species. Warm and humid conditions allowed animals to grow larger and flourish in great numbers. Vegetation grew rapidly, providing abundant food and shelter. Seasonal variations in rainfall encouraged migrations and adaptations, while occasional dry periods tested the survival skills of animals and plants. This environment favoured creatures that could move across large distances, store food or water, or exploit temporary habitats created by seasonal changes. Over millions of years, the combination of stable warmth, high humidity, and periodic dry seasons shaped the evolution of the ecosystems, leading to a rich diversity of species both on land and in the water. Geographic features also influenced local climates. Mountains affected wind patterns and rainfall, coastal plains were exposed to storms and high humidity, and inland valleys could be drier than surrounding areas. The breakup of the supercontinent gradually changed ocean and wind currents, creating new climate zones and altering rainfall distribution. This shifting landscape meant that the climate was dynamic over long periods, slowly changing as continents moved and seas expanded or contracted. Insects and small animals were directly affected by the humid climate. High humidity helped them survive, reproduce, and spread across wide areas. Amphibians, which rely on moisture, thrived, especially in wet forests and swamps. Reptiles adapted to various climates, some living in humid forests while others survived in drier inland areas. Birds and mammals, which were just beginning to appear, had to cope with the warm, wet conditions as well as seasonal changes in rainfall. The overall climate during this era was one of warmth, humidity, and seasonal variability, shaping every aspect of life on Earth. It influenced the size and distribution of plants, the movement and behavior of animals, and the formation of landscapes and water bodies. Rivers, lakes, and seas were affected by rainfall and temperature. Coastal areas were shaped by storms, and inland regions experienced the effects of dry seasons. All life had to adapt to these conditions, leading to the evolution of new forms, the migration of species, and the establishment of complex ecosystems. The interaction between temperature, humidity, rainfall, and geography created a world that was very different from the modern Earth, yet it was rich, dynamic, and full of life, with each region having its own distinct climate patterns and seasonal rhythms. The combination of high carbon dioxide levels, warm oceans, absence of polar ice, and the slowly shifting continents created a climate that was consistently warm and humid over millions of years. Dry seasons occurred occasionally, but they were often localized and short compared with the long periods of wet and warm conditions. This climate allowed life to expand into regions that would be uninhabitable today, supporting enormous reptiles, vast forests, and abundant marine life. Seasonal variations dictated much of the behavior of animals and growth cycles of plants, while extreme weather events, although rare, shaped the landscape and influenced evolution. Mountains, rivers, and seas all interacted with the climate, producing a complex mosaic of habitats, each with unique conditions of temperature, moisture, and seasonal change. Rivers, lakes, and inland seas were shaped directly by the climate, with warm temperatures increasing evaporation and humidity leading to frequent rains. These water sources were vital for the survival of animals, especially during dry periods, and they provided fertile ground for plants. Floodplains and wetlands developed in areas with consistent rainfall, supporting dense forests and diverse ecosystems. In drier areas, seasonal water availability led to migration and adaptation among animals, with life concentrating near reliable sources of water. The climate's warmth and humidity allowed for rapid growth and reproduction. Plants could photosynthesize more efficiently in the warm, moist air, and animals had a continuous supply of food. Insects multiplied in large numbers, amphibians thrived in swampy conditions, and reptiles could grow to enormous sizes. The dynamic interplay between wet and dry seasons, along with occasional extreme weather, created a constantly changing environment where only the most adaptable species could thrive. High humidity also affected the soil. Continuous rainfall caused nutrients to wash into rivers and lakes, creating rich floodplains. In some areas, the combination of warmth and moisture accelerated the breakdown of rocks into fertile soil. These fertile lands allowed forests to expand and provided food for herbivorous animals. Swamps and wetlands retained water even during drier periods, offering refuge for aquatic and semi-aquatic life. The warm and humid climate influenced the evolution of many species. Large reptiles evolved to take advantage of abundant food and water, while plants developed ways to thrive in constant moisture or withstand occasional dry spells. Seasonal variations in rainfall encouraged migration and dispersal of species, leading to interactions and competition that drove evolutionary change. The abundance of water and warmth provided the conditions necessary for life to diversify, leading to ecosystems with many different plants and animals coexisting in a relatively small area. Coastal and marine ecosystems were particularly affected by the climate. Warm seas encouraged the growth of coral reefs and the expansion of marine plants. Ocean currents, influenced by warm temperatures and winds, distributed nutrients across large areas, supporting large populations of fish, shellfish, and marine reptiles. Storms occasionally reshaped coastlines, depositing sediments and creating new habitats. Shallow inland seas and lagoons, warmed by the climate, provided safe havens for fish and other marine life, while rivers carried nutrients from inland areas to the oceans, maintaining a rich and productive marine environment. Wind, temperature, and rainfall combined to create local climates that varied widely across the continents. Coastal areas experienced high humidity and frequent storms, lowlands and river valleys were lush and wet, and uplands and inland regions had more seasonal variation. Mountains influenced rainfall patterns, creating drier regions on their leeward sides. These variations meant that the climate was not uniform, and different areas provided different conditions for life. Some regions remained wet throughout the year, supporting dense forests, while others experienced seasonal dryness that required adaptation and migration. Overall, the climate of this period was characterized by consistent warmth, high humidity, and seasonal variability in rainfall. This combination influenced plant growth, animal behavior, and the development of ecosystems. Rivers, lakes, seas, and wetlands were shaped by rainfall and temperature. Mountains and wind patterns created local variations, and seasonal changes dictated the cycles of life. The warm, humid conditions allowed life to expand into regions that are now too cold or dry to support such diversity, while dry periods and extreme weather events created challenges that drove adaptation and evolution. The high temperatures and humidity influenced the spread of species across continents. Plants and animals could inhabit areas far from the equator, with tropical and subtropical conditions extending into regions that are now temperate or even cold. Seasonal dry periods created pressures that encouraged migration, while wet seasons supported rapid growth and reproduction. The combination of warmth, humidity, and water availability made the world highly productive, supporting large populations and a wide diversity of life. The climate patterns were dynamic, influenced by geography, ocean currents, atmospheric composition, and the slow movement of continents. The warm, humid conditions remained dominant, but periodic dry seasons, storms, and volcanic activity created variability. Rivers, lakes, and inland seas provided stability during dry periods, and fertile soils supported abundant vegetation. Large reptiles, amphibians, and early mammals thrived in this environment, while insects and other invertebrates multiplied rapidly. The climate allowed ecosystems to flourish, with complex interactions between plants, animals, water, and land shaping the natural world over millions of years. The interaction between temperature, humidity, rainfall, and geography resulted in a variety of habitats. Wetlands and marshes provided refuge for amphibians and reptiles. Forests supported herbivores and predators, and rivers and lakes acted as centers of life during dry periods. Coastal regions experienced storms that reshaped the land, while inland areas depended on seasonal rains to maintain water sources. These climate patterns created opportunities for life to diversify, adapt, and evolve, producing ecosystems that were complex, resilient, and highly productive. The climate also influenced migration and dispersal. Animals moved to take advantage of seasonal rainfall, while plants spread to colonize new areas. Warm temperatures allowed rapid growth and reproduction, while high humidity created favorable conditions for amphibians, insects, and reptiles. Even during dry seasons, rivers and lakes provided refuges, allowing life to persist in otherwise challenging conditions. Over millions of years, these climatic conditions shaped the distribution of species, the structure of ecosystems, and the patterns of evolution, producing a world that was warm, humid, and teeming with life across almost every region of the globe. This period of Earth's history demonstrates how climate, temperature, humidity, and rainfall combined to create an environment that was fundamentally different from the modern world. Life was able to flourish in areas that are now far too cold or dry, while periodic dry seasons created pressures that drove adaptation and evolution. Rivers, lakes, seas, wetlands, and forests all responded to the climate, creating a dynamic and productive natural world. Warm oceans, high atmospheric carbon dioxide, and the absence of polar ice ensured that temperatures remained high and humidity persisted, making it possible for lush forests, abundant water sources, and diverse animal populations to exist across the planet. The interplay between weather and geography shaped every aspect of life. Winds brought moisture inland, oceans distributed heat, rainfall fed rivers and wetlands, and mountains influenced local climates. Seasonal variation in precipitation dictated migration and growth patterns, while occasional dry periods tested the resilience of plants and animals. Coastal areas faced storms that altered landscapes, while inland valleys depended on rivers and lakes to survive. The climate created both opportunities and challenges, fostering adaptation, evolution, and the expansion of life into new areas. The climate's warmth and humidity, combined with occasional dry seasons, allowed ecosystems to be productive and resilient. Plants could grow rapidly, herbivores had abundant food, and predators could support large populations. Amphibians and reptiles thrived, insects multiplied, and early mammals navigated the warm, wet, and seasonally variable conditions. Water bodies played a central role in sustaining life, especially during dry periods, while fertile soils encouraged the spread of forests and other vegetation. Even as the continents slowly moved and oceans shifted, the warm, humid climate persisted. Seasonal dry periods created cycles that influenced growth, reproduction, and migration. Rivers and lakes maintained life during droughts, while storms redistributed sediments and shaped coastlines. Warm temperatures and high humidity allowed life to expand into areas that are now too cold or dry, and the dynamic interplay between climate, geography, and life ensured that ecosystems remained productive, complex, and diverse. The persistent warmth, high humidity, and occasional dry seasons shaped the evolution of countless species. Large reptiles grew to enormous sizes, amphibians thrived in moist environments, insects multiplied rapidly, and early mammals began to diversify. Plants adapted to the wet and dry cycles, with forests dominating the landscape and wetlands forming in low-lying areas. Over vast stretches of time, the world's oceans have not stayed still or constant. The seas have risen and fallen, sometimes covering vast areas of the continents, and sometimes retreating to reveal land that had been hidden beneath water for millions of years. During certain periods, sea levels were remarkably high, much higher than they are today. The rising waters did not simply form narrow coastlines, but often flooded enormous regions, creating shallow seas that spread deep into the land, known to scientists as epicontinental seas. These shallow seas were extensive, sometimes stretching for hundreds of kilometers inland, transforming landscapes that would otherwise have been dry into wide watery realms. In some regions, they covered entire plains, filling valleys and lowlands and creating vast networks of shallow water bodies connected to the larger oceans. The water in these seas was usually not very deep compared to today's oceans, but it was broad, warm, and teeming with life. The shallow depth allowed sunlight to reach the seafloor across vast areas, enabling marine plants and algae to flourish. Unlike the deep ocean, where light cannot penetrate beyond a certain point, these shallow epicontinental seas allowed photosynthetic organisms to thrive, forming the foundation for complex food webs. Plankton and small algae drifted near the surface, feeding a multitude of tiny animals which in turn became food for larger predators. The expansion of these seas over the continents changed the way life evolved. Many marine organisms that lived close to shore found new habitats as the seas spread, giving them opportunities to explore regions that had once been land. Coral reefs, for example, could extend farther and create massive reef complexes where fish and other marine creatures could hide, feed, and reproduce. Mollusks, crabs, and other shell-bearing creatures thrived in these shallow waters, often leaving fossil evidence that helps modern scientists understand how widespread these seas were. The shape of coastlines changed as well. Instead of jagged and narrow shorelines, the high sea levels often produced wide, gentle slopes, with soft sediments that provided ideal conditions for organisms to burrow, feed, and reproduce. Some regions that were previously mountainous or forested were partially submerged, transforming terrestrial ecosystems into watery landscapes, where amphibious life forms and semi-aquatic creatures found temporary or permanent habitats. Rivers flowing into these seas carried sediment, nutrients, and organic matter from the land, enriching the shallow waters and encouraging the growth of plankton and other tiny organisms. The sediment itself often settled to the seafloor, creating soft, muddy bottoms that were perfect for burrowing worms, clams, and other benthic creatures, which became part of the intricate food web that connected all levels of life in these waters. The variations in sea level also had a profound impact on the connectivity of different marine populations. When the seas rose and epicontinental regions flooded, marine animals could move freely across areas that had once been isolated, allowing species to spread over enormous distances. Fish, ammonites, and other swimming organisms could travel further, colonizing new habitats and mixing with populations from distant regions. In contrast, when sea levels dropped, these connections were reduced or lost entirely, isolating populations and leading to speciation events as separate groups adapted to different environmental conditions. This ebb and flow of water created dynamic ecosystems in which competition, predation, and adaptation occurred continuously, shaping the evolutionary history of countless species. The wide coverage of epicontinental seas also influenced the chemistry of the oceans. Large shallow seas tended to have different temperatures and salinity levels compared to the open ocean. The warmer waters of shallow regions allowed certain species to flourish, while limiting others that preferred cooler, deeper waters. Variations in salinity created unique conditions for life, with some organisms adapting to brackish waters that formed where rivers met the shallow seas. These conditions fostered evolutionary innovations, as creatures had to cope with changes in temperature, water depth, and salinity. The sedimentation processes in shallow seas left a lasting mark on Earth. Over millions of years, the accumulation of sand, silt, and clay in epicontinental regions created layers of sedimentary rock that often contained rich fossil records. Fossils preserved in these deposits provide a window into the past, showing the diversity of marine life that once inhabited shallow seas. Ammonites with their coiled shells, belemnites with their bullet-shaped bodies, brachiopods, trilobites, and many other organisms left behind hard parts that were gradually buried under sediment and preserved for future study. Some of these layers also contain evidence of large-scale environmental changes, such as shifts in water temperature, sea level fluctuations, and even episodes of anoxia, where oxygen levels in the water dropped dramatically. These events sometimes caused mass die-offs in shallow seas, which in turn affected the evolution of surviving species. The shallow seas were often hotspots of biodiversity. Because they were generally warm and well lit, they could support a wide range of life forms simultaneously. This included microscopic plankton, which formed the base of the food chain, as well as larger predators like ichthyosaurs and plesiosaurs in later periods, which hunted the abundant smaller creatures. Sea turtles, early crocodile relatives, and various kinds of fish exploited these waters as well, while large flying reptiles and birds sometimes hunted along the shores. The combination of shallow waters, ample sunlight, and nutrient-rich sediments created conditions where evolutionary experimentation could occur on a scale far beyond what might be found in deeper, more stable parts of the ocean. The movement of tectonic plates over millions of years also contributed to the changes in sea level and the formation of epicontinental seas. As continents drifted and ocean basins shifted, the volume of the oceans changed and certain regions sank while others rose. When a continental landmass subsided, water from the oceans could spread across it, forming shallow seas that lasted for millions of years. Conversely, when uplift occurred, seas retreated, leaving behind sedimentary deposits that recorded the history of the temporary inundation. This constant reshaping of the Earth's surface affected not only marine life, but also the climate, weather patterns, and river systems, which in turn influenced how nutrients and sediments were delivered to the seas. Because of the shallow nature of epicontinental seas, they were particularly sensitive to changes in climate. Warmer periods could expand these seas further inland, while cooler or drier periods could shrink them. Changes in rainfall, evaporation rates, and river flow also affected the salinity and depth of these waters, influencing which species could survive and which could not. This interplay of physical conditions and biological responses created complex ecological networks that shifted over time, allowing scientists to trace the history of life and environmental change through the fossil record. The presence of epicontinental seas influenced coastal ecosystems as well. Shores that were once exposed to air became shallow bays and lagoons, providing new habitats for organisms that lived both in water and on land. Crustaceans, mollusks, and amphibious vertebrates could exploit these new environments, often finding safety from predators that were confined to deeper waters. These zones were also important for the reproduction of many marine species, as shallow waters offered warmer and more protected conditions for laying eggs and nurturing young. Migratory species could use these seas as stopovers during long journeys, while resident species could specialize in exploiting the particular conditions of these shallow regions. Ocean currents and tides played an important role in shaping life in epicontinental seas. Although the waters were shallow, currents could distribute nutrients and larvae over wide areas, allowing species to colonize new regions and maintain genetic diversity. Tidal fluctuations often created periodic exposure and submersion of parts of the seabed, which could stress some organisms but provide opportunities for others. Certain burrowing and filter-feeding species thrived under these conditions, taking advantage of nutrient pulses brought in by tides and currents. The constant movement of water ensured that these ecosystems were dynamic, with opportunities for both growth and survival constantly shifting over time. Shallow seas also acted as crucial links between different parts of the oceans. Unlike the deep ocean, which can isolate populations due to vast distances and depth, epicontinental seas allowed relatively easy movement of species between regions. This connectivity meant that evolutionary trends could spread quickly, and organisms could encounter new competitors, predators, and prey. The spread of marine organisms through these seas contributed to the high levels of biodiversity recorded in the fossil record. At times, the seas connected distant ocean basins, allowing the mixing of species from different evolutionary lineages. This mixing could result in the emergence of entirely new forms of life, as organisms adapted to novel ecological pressures. The interactions between shallow seas and the atmosphere also shaped the chemistry of the oceans. Warm, shallow waters facilitated evaporation, which affected local climate and rainfall patterns. Increased evaporation could raise salinity levels in certain areas, creating hypersaline environments where only specially adapted organisms could survive. Rainfall and river inflow, on the other hand, could dilute these waters, creating gradients of salinity that supported a range of life from freshwater-tolerant species to true marine organisms. This variability contributed to the diversity of habitats and ecological niches available in epicontinental seas, encouraging specialization and adaptation. Sediment deposits in these shallow seas were often layered with remarkable detail, recording subtle changes in environment over time. Fossilized shells, plant remains, and trace fossils of burrows, feeding marks, and trackways provide rich evidence of the interactions between organisms and their environment. These sediments reveal not only who lived there, but also how conditions such as water depth, temperature, salinity, and nutrient levels fluctuated over time. By studying these layers, scientists can reconstruct the pace of environmental change, the migration of species, and the rise and fall of communities. In some regions, thick sequences of sediment record millions of years of sea level changes, showing repeated cycles of flooding and retreat that correspond to global climatic shifts, tectonic events, and changes in oceanic currents. The fossil evidence preserved in these sediments also demonstrates the role of shallow seas in evolution. Many groups of organisms show bursts of diversification during periods when epicontinental seas expanded, while declines and extinctions often occurred when the waters receded. The interplay between rising seas, sedimentation, and ecological opportunity created conditions where evolution could accelerate, generating forms of life that might never have existed otherwise. The shallow seas also influenced the chemistry of the oceans over long periods. As rivers carried minerals and organic matter into these seas, they enriched the water with nutrients that fueled plankton blooms. The organic matter that settled to the seafloor was buried by successive layers of sediment, locking away carbon and affecting the global carbon cycle. periodic oxygen depletion events in the bottom waters of these seas could result in the preservation of finely detailed fossils, known as Lagerstätten, where even soft-bodied creatures could be fossilized. Such deposits offer extraordinary windows into ancient ecosystems, revealing creatures that are rarely preserved elsewhere. In addition, the interaction between shallow seas and the atmosphere contributed to local and global climate patterns. The presence of broad, warm waters could moderate temperatures on nearby land, while the high evaporation rates could drive rainfall patterns that influenced river flows and nutrient delivery. The shallow seas were thus part of a larger system connecting the oceans, the land, and the atmosphere in a continuous cycle that shaped the evolution of both marine and terrestrial life. Over millions of years, the configuration of continents and the extent of epicontinental seas changed repeatedly. In some periods, high sea levels allowed these shallow seas to stretch across entire continental interiors, while at other times, seas retreated to narrow coastal zones, isolating populations and creating new selective pressures. These cycles created a dynamic evolutionary landscape, where species had to adapt constantly to changing habitats, shifting food sources and new competitors. Shallow seas acted as both highways and barriers, connecting some populations while isolating others, influencing migration, reproduction, and speciation. This constant reshaping of the marine environment helped drive the rich diversity of life that is recorded in the fossil record. In many regions, the remnants of epicontinental seas can still be observed in the rock record, revealing extensive sequences of limestone, shale, and sandstone that were laid down in shallow water over millions of years. Fossils embedded in these rocks tell the stories of ancient seas, from tiny plankton to large marine reptiles, showing how these waters nurtured life, created ecological opportunities, and recorded the ongoing interaction between biology and the physical world. The shallow epicontinental seas were often sites of intense biological activity. Large numbers of fish, invertebrates, and marine reptiles crowded these waters, creating intricate food webs where energy flowed from the smallest organisms to the largest predators. Coral reefs and shell beds provided shelter and feeding grounds, while open water areas supported schooling fish and predatory species. The variety of habitats within these seas, from mudflats and lagoons to reef complexes and open shallow waters, created numerous niches for life to exploit. The dynamics of predation, competition, and reproduction in these environments were influenced directly by water depth, clarity, temperature, and nutrient availability. Over time, the repeated flooding and retreat of these seas also created opportunities for organisms to colonize new areas or retreat to refuges when conditions became unfavorable. In addition to supporting complex ecosystems, epicontinental seas played a role in the global distribution of life. Because these shallow waters often connected distant marine regions, species could migrate over long distances, spreading their genes and influencing evolutionary patterns on a continental scale. When seas receded, some populations became isolated, promoting the development of new species as organisms adapted to local conditions. This interplay of connection and isolation, abundance and scarcity, was a key driver of the diversity of marine life observed in the fossil record. Shallow seas also interacted closely with the organisms living on land near their margins. Coastal areas and deltas were often heavily influenced by the tides and waves of these inland seas, shaping soil conditions, nutrient flows, and vegetation patterns. Animals that lived near these shores had to contend with fluctuating water levels, while some species adapted to exploit the interface between land and sea, feeding on both aquatic and terrestrial resources. The ecological connections between land and sea were especially important in times when epicontinental seas expanded, creating temporary wetlands, lagoons, and estuaries where terrestrial and marine species could interact. Rivers flowing into these shallow seas transported sediments and nutrients, creating productive areas where plankton, fish, and other organisms thrived. These zones often served as nurseries for juvenile creatures, providing food and shelter that increased survival rates and helped maintain population stability. The patterns of sediment deposition in these areas also contributed to the formation of rich fossil deposits, preserving evidence of the interplay between marine and terrestrial ecosystems. The expansion of epicontinental seas often coincided with periods of high global temperatures. Warm climates encouraged the spread of shallow seas over the continents and created hospitable conditions for a wide range of organisms. Tropical and subtropical conditions dominated many of these regions, supporting coral reefs, diverse mollusk communities, and abundant planktonic life. These warm seas encouraged rapid growth and reproduction in many species, leading to dense populations and complex interactions among organisms. Conversely, cooler periods could cause sea levels to drop, retreating the seas and altering habitats dramatically. Species that thrived in one period might struggle in the next, leading to evolutionary pressures that favoured adaptability and resilience. Over long stretches of geologic time, the cyclical expansion and contraction of epicontinental seas, driven by changes in sea level, climate, and tectonic activity, created a dynamic and ever-changing marine environment. Life in these waters was shaped by constant interactions between physical and biological forces, including sunlight, temperature, salinity, sedimentation, currents, tides, and the availability of food. These interactions produced extraordinary opportunities for evolution, speciation, and diversification, resulting in ecosystems that were both rich and fragile. Fossils preserved in the sediments of these ancient shallow seas allow scientists today to reconstruct the history of marine life, the chemistry of the oceans, and the patterns of environmental change over millions of years. The effects of high seas and shallow epicontinental seas extended far beyond the water itself, influencing land ecosystems, climate systems, and global cycles of nutrients and carbon, leaving a legacy that can still be traced in rocks, fossils, and the distribution of ancient marine species. The life that flourished in epicontinental seas was remarkably diverse. Invertebrates like ammonites, nautiloids, brachiopods, and mollusks dominated many regions, forming dense populations in shallow waters. These creatures often lived in colonies, attached to the seafloor or buried in sediments, filtering food from the water or preying on smaller organisms. Vertebrates such as early fish, marine reptiles, and later, large predatory dinosaurs that ventured into coastal waters took advantage of the abundance of food and the protection offered by shallow waters and reefs. Planktonic organisms formed the base of the food chain, and their abundance allowed the rapid growth of larger animals. Over time, the interactions among these creatures, combined with changes in sea level and environmental conditions, created a dynamic ecosystem that was constantly evolving. Epicontinental seas also affected patterns of sediment transport and deposition. Rivers carried vast quantities of silt, clay, and sand into these shallow waters, creating deltas, mudflats, and other depositional features. Tides and currents redistributed these sediments, forming layered deposits that record the environmental conditions of the time. Fossils preserved in these sediments reveal the composition of ancient communities and provide clues about the climate, water depth, and nutrient levels. These deposits often preserve entire ecosystems in astonishing detail, including both hard-shelled and soft-bodied organisms, allowing scientists to reconstruct ancient food webs, migration patterns, and ecological interactions. The shallow seas influence not only the distribution of life, but also the chemistry of the oceans, the climate of nearby land masses, and the evolution of marine species. The shallow epicontinental seas played a critical role in connecting ecosystems across vast distances. Because these seas often extended across continents or linked separate ocean basins, they allowed species to move and mix in ways that were not possible in deeper, more isolated waters. This connectivity facilitated gene flow, reduced the risks of inbreeding, and allowed species to colonize new areas. At the same time, the repeated flooding and retreating of these seas created opportunities for isolation, driving the formation of new species and increasing biodiversity. The interaction of these physical and biological processes over millions of years produced some of the most productive and diverse marine ecosystems in Earth's history. Over hundreds of millions of years, the rise and fall of epicontinental seas continued to shape the evolutionary and geological history of the planet. These shallow seas were not static environments, but dynamic systems where life, sediment, and water interacted in complex and fascinating ways. They were places of abundance and danger, of growth and extinction, where organisms adapted, thrived, and sometimes vanished, leaving behind a record that continues to inform our understanding of the history of life on Earth. The interplay between high seas, shallow waters, and marine life created a world that was constantly changing, full of opportunities for survival, competition, and adaptation, and it left an enduring imprint on the oceans, continents, and the living world. These seas had important consequences for the distribution of minerals and resources. Shallow seas often concentrated calcium, silica, and other minerals in their sediments, which over time formed limestone, chert, and other sedimentary rocks. These rocks contained fossilized shells and skeletons, serving as records of ancient marine life. The sediments also trapped organic material, which could later form coal or oil deposits, providing crucial resources for future generations. The interaction of water, sediment, and life in these shallow seas helped shape the chemical and geological landscape of the Earth, producing layers that reveal patterns of environmental change over millions of years. The fluctuating coverage of epicontinental seas also played a role in the formation of ancient climates. Broad, shallow seas could moderate temperatures in nearby areas, reducing extremes of heat and cold on adjacent lands. The waters absorbed heat during the day and released it slowly at night, creating more stable temperature patterns along coasts and inland areas that were temporarily flooded. These temperature buffers influenced weather patterns, rainfall distribution, and even wind currents, indirectly affecting terrestrial ecosystems. Regions that were alternately submerged or exposed experienced cycles of soil wetness and dryness, influencing plant growth and the types of vegetation that could survive. Wetland plants and aquatic vegetation thrived in areas that remained under shallow water for extended periods, while more drought-tolerant species colonized the higher lands exposed during sea retreats. This constant alternation between water coverage and exposure contributed to the creation of rich and diverse ecosystems, both on land and in the sea, enhancing the interplay between marine and terrestrial life. Marine life in shallow seas often experienced bursts of population growth during periods of stable conditions. The combination of abundant sunlight, nutrient-rich waters, and warm temperatures created ideal conditions for rapid reproduction. Planktonic blooms provided a constant supply of food for small fish, crustaceans, and other invertebrates, which in turn supported larger predators. These periods of abundance often coincided with the deposition of thick sedimentary layers, preserving an extraordinary record of life that can be studied millions of years later. Fossil evidence from these layers shows both diversity and specialization, revealing organisms adapted to very specific conditions within these shallow seas, from tidal flats and lagoons to reefs and open shallow waters. Predatory dynamics in epicontinental seas were shaped by the shallow nature of the water. Predators such as marine reptiles, early sharks, and large predatory fish could hunt effectively because prey species were confined to relatively narrow sunlit zones, making hunting more predictable. Similarly, prey species developed adaptations such as burrowing, camouflage, or schooling behavior to avoid predation. Sheltered bays, coral structures, and mudflats offered hiding places, creating microhabitats that further contributed to biodiversity. The interactions between predators and prey in these environments were more immediate and intense than in the open ocean, where deeper waters allowed escape routes and reduced encounters. Shallow seas also played a crucial role in the dispersal of nutrients. Rivers flowing into these seas carried minerals and organic matter, which fueled plankton growth. Waves and tidal movements spread nutrients across the seafloor, allowing benthic communities to thrive. The decomposition of organic material in sediments released additional nutrients back into the water, sustaining the food web. This continuous cycling of matter maintained high productivity in shallow seas, supporting dense populations of animals and promoting evolutionary experimentation. Even the tiniest organisms, such as microorganisms and plankton, contributed significantly to these cycles, ensuring that energy flowed efficiently from the bottom to the top of the food chain. The connectivity provided by epicontinental seas allowed the spread of species across vast distances. When high seas linked distant shallow basins, species could migrate freely, mixing with other populations. This gene flow reduced inbreeding and introduced new genetic variations, which could enhance adaptability and resilience. In contrast, when seas receded, populations became isolated, and natural selection acted more strongly on local adaptations. This cycle of connectivity and isolation helped drive diversification and speciation, making epicontinental seas hotspots of evolutionary innovation. The physical characteristics of these shallow seas influenced the evolution of life in ways that are still evident today. Sunlight penetration favored photosynthetic organisms, which formed the basis of complex food webs. Temperature gradients allowed species to occupy specific niches, and variations in salinity led to adaptations that enabled life to survive in brackish or fluctuating environments. Water depth influenced mobility, with some organisms evolving strong swimming capabilities while others specialized in burrowing or living attached to the seafloor. Even the softness or hardness of sediments dictated the types of organisms that could inhabit particular areas, promoting diversity through habitat specialization. Over millions of years, epicontinental seas fluctuated with global changes in climate and tectonic activity. Warm periods generally cause sea levels to rise, extending these shallow waters across continents. Cooler periods or glaciations cause sea levels to fall, exposing former seabeds and creating new landforms. These cycles resulted in alternating periods of expansion and contraction, forcing organisms to adapt to new conditions repeatedly. Species that could tolerate a range of environmental conditions had a higher chance of survival, while others either migrated or faced extinction. Fossils from these periods document these changes, providing detailed insights into how life responded to shifting seascapes. The ecological role of epicontinental seas was further amplified by their effects on carbon cycling. Shallow seas facilitated the burial of organic material in sediments, which over time became fossil fuels such as coal and oil. The sequestration of carbon in these deposits influenced global climate patterns, affecting the atmosphere and regulating temperatures over geological timescales. Periods of high sea levels and widespread epicontinental seas often coincided with major carbon burial events, leaving a lasting imprint on Earth's climate and the composition of the oceans. Epicontinental seas were also critical in shaping evolutionary pathways for specific groups of animals. Mollusks, for instance, diversified extensively in these shallow waters, developing a range of shell forms and feeding strategies. Coral communities expanded and built extensive reef systems that supported a wide array of invertebrates and fish. Marine reptiles adapted to the abundance of prey in shallow seas, evolving specialized teeth, flippers, and body forms for hunting and swimming efficiently in these environments. Fish evolved different shapes, sizes, and feeding strategies to exploit the varied niches available, demonstrating the close link between environmental conditions and evolutionary innovation. The dynamic nature of shallow seas created feedback loops that affected both biology and geology. Organisms influenced sediment deposition by burrowing, feeding, and constructing shells, which in turn affected the physical characteristics of the seafloor. The seafloor, shaped by sediments and biological activity, influenced water flow, nutrient distribution, and habitat availability. This continuous interplay between life and the physical environment maintained ecosystem productivity and complexity over millions of years. Changes in water levels, sediment supply, and climate triggered shifts in this balance, producing periods of rapid change and adaptation. Epicontinental seas were often zones of intense evolutionary pressure. Competition for food, shelter, and mating opportunities was fierce in these productive environments. Predators could encounter prey easily, and prey species had to develop effective defenses. Rapid population growth and high reproductive rates created opportunities for mutations and adaptations to spread quickly through populations. These factors contributed to bursts of evolutionary innovation, resulting in species with specialized behaviors, structures, and ecological roles that were finely tuned to their environments. Fossil records show that many modern groups of organisms have ancestors that thrived in epicontinental seas, highlighting the enduring influence of these shallow waters on life's evolutionary trajectory. The interaction between shallow seas and the atmosphere also influenced regional climates. Large bodies of warm, shallow water could increase humidity in adjacent land areas, promoting rainfall and the development of wetlands. Evaporation from the seas contributed to cloud formation and local weather systems, creating conditions favorable for terrestrial and aquatic plants alike. The climate moderation provided by these seas sometimes allowed species to persist in regions that would have been inhospitable under more extreme conditions. This connection between shallow seas, climate, and ecosystems underscores the complex interdependence of life and environment over geologic time. Sediment layers in epicontinental seas preserve extraordinary detail about past ecosystems. Fossils embedded within these layers reveal predator-prey relationships, reproductive behaviors, and patterns of migration. Trace fossils such as burrows, feeding marks, and footprints provide evidence of animal behavior and interactions, giving a more complete picture of life in shallow seas than body fossils alone. These deposits also record environmental conditions such as water depth, temperature, and salinity, allowing scientists to reconstruct past climates and understand how species adapted to changes over time. The frequent flooding and retreat of epicontinental seas created a patchwork of habitats, each with its own set of ecological pressures. Species had to be versatile to survive across different zones, or they specialized in a particular niche. Mudflats, lagoons, reefs, open shallow waters, and coastal plains each offered distinct opportunities and challenges. Some species moved seasonally between habitats, while others remained confined to specific areas, resulting in a mosaic of biodiversity. The alternation between connectivity and isolation provided by changing sea levels promoted genetic diversity and speciation, producing the rich array of life documented in the fossil record. Even small changes in sea level could have dramatic effects on these ecosystems. A few meters of rise or fall could flood large areas or expose previously submerged land, altering habitats and forcing species to relocate or adapt. Organisms that could move or tolerate changing conditions had an advantage, while less adaptable species faced increased mortality. This constant pressure drove evolutionary innovation, favoring traits such as mobility, burrowing, and tolerance of varying salinity and temperature. The cyclical nature of sea level change ensured that these selective pressures operated over millions of years, shaping the evolutionary trajectory of many marine groups. Epicontinental seas also facilitated the transport of organisms and genetic material across wide distances. Ocean currents, tides, and river inflows carried larvae, plankton, and small animals from one region to another, connecting populations that would otherwise have been isolated. This dispersal allowed species to colonize new areas, maintain genetic diversity, and respond to environmental changes. When seas retreated, some populations became isolated, creating conditions for rapid evolutionary divergence. These cycles of connectivity and isolation, driven by sea level changes, were fundamental in shaping the diversity of life in shallow seas. The shallow nature of epicontinental seas made them particularly vulnerable to environmental fluctuations. Storms, temperature swings, and changes in sediment load could alter habitats quickly. Organisms had to cope with these changes or risk extinction. The resilience of species in these environments depended on their ability to exploit different resources, move to suitable habitats, and reproduce successfully under variable conditions. Over time, these pressures led to the evolution of highly specialized adaptations and behaviors, allowing species to survive and even flourish despite environmental challenges. The sediments of epicontinental seas provide an enduring record of these complex ecosystems. Layers of limestone, shale, sandstone, and other deposits contain fossils of invertebrates, fish, reptiles, and plants, as well as evidence of microbial life. These fossils show not only which species existed, but also how they interacted, what they ate, and how they moved through their environments. Trace fossils reveal burrowing behaviors, feeding patterns, and reproductive strategies, providing a detailed picture of ancient life. The sedimentary record also preserves evidence of sea level fluctuations, climate change, and nutrient cycles, offering insights into the forces that shape the evolution of life in shallow seas. Life in epicontinental seas was a constant interplay between opportunity and challenge. The abundance of food, shelter, and sunlight created opportunities for growth and diversification, while changing sea levels, predators, and environmental variability imposed challenges that demanded adaptation. The evolutionary pressures generated by these dynamic conditions produced some of the most diverse and productive ecosystems in Earth's history. Species that thrived in these environments contributed to the richness of the fossil record and laid the groundwork for modern marine biodiversity. The cyclical rise and fall of epicontinental seas, driven by tectonic movements, climate change, and oceanic processes, created a world of constant change. These shallow seas were both a stage for evolutionary innovation and a record of environmental history. The interactions between water, sediments, organisms, and climate shaped the development of marine life, the deposition of sediments, and the evolution of coastal and terrestrial ecosystems. Fossils preserved in the sediments of epicontinental seas continue to reveal the story of life in shallow waters, showing how these high seas influence the history of Earth's oceans, climate, and biodiversity. Shallow seas created environments where marine life could diversify, adapt, and spread across the globe. The combination of sunlight, warmth, and nutrient availability allowed photosynthetic organisms, plankton, invertebrates, and vertebrates to thrive. Predation, competition, and reproductive pressures drove evolution and specialization, producing a rich tapestry of life. The sediments deposited in these seas preserved this life for millions of years, providing detailed evidence of ecosystems, behaviors, and environmental conditions. The dynamic nature of epicontinental seas, with their cycles of expansion and retreat, created both challenges and opportunities, shaping the evolutionary history of the oceans and leaving a lasting imprint on the planet. High seas and epicontinental waters were instrumental in connecting distant regions and enabling the dispersal of life across continents. Currents, tides, and river systems transported organisms and nutrients, while shallow waters provided refuge, breeding grounds, and feeding opportunities. The constant interplay between connectivity and isolation promoted genetic diversity, speciation, and the spread of evolutionary innovations. These seas influenced not only marine ecosystems, but also the climate, sedimentation, and chemistry of the oceans. Their legacy can be seen in fossil-rich sedimentary layers, the distribution of ancient species, and the evolutionary patterns that continue to shape life on Earth. The interaction of life with shallow epicontinental seas was complex and continuous. From microscopic plankton to large marine reptiles, organisms exploited the abundant resources and adapted to environmental fluctuations. Predation, competition, reproduction, and dispersal shaped communities, while sedimentation and water chemistry recorded their presence for future generations to study. The seas acted as arenas of evolutionary change, where life experimented, adapted, and evolved over millions of years. The rich fossil record of these shallow waters provides an unparalleled window into the past, revealing not only the diversity of life, but also the intricate relationships between organisms and their environment in high seas and epicontinental waters. The coverage of the continents by shallow seas at various points in Earth's history was vast, sometimes reaching hundreds of kilometers inland, creating a patchwork of marine habitats interspersed with exposed land. These environments influenced the development of coastal vegetation, sediment deposition, and nutrient cycling. The proximity of land provided additional resources to shallow seas through river inflows, terrestrial runoff, and nutrient-rich sediments. This connection between land and water further enriched ecosystems, promoting diversity and complex interactions among species. The fossil evidence preserved in epicontinental seas highlights the importance of these environments in evolutionary history. The remains of mollusks, brachiopods, corals, fish, marine reptiles, and other organisms reveal a world of remarkable diversity and adaptation. Trace fossils, including burrows, feeding marks, and reproductive structures, document behaviors that would otherwise be lost. Sediment layers record changes in water depth, climate, salinity, and nutrient availability, offering a detailed chronology of environmental change. Together, these records show how shallow seas influence the evolution of life, the deposition of sediments, and the dynamics of ecosystems over millions of years. The dynamic and ever-changing nature of shallow epicontinental seas created conditions that were both challenging and supportive for life. Rising and falling sea levels, fluctuating temperatures, variable salinity, and shifting sediments forced organisms to adapt or perish. These pressures led to evolutionary innovations, ecological specialization, and the diversification of life forms. At the same time, the abundance of sunlight, warmth, and nutrients provided opportunities for growth, reproduction, and survival. This balance of challenge and opportunity shaped the ecological and evolutionary history of marine life, leaving an enduring legacy preserved in the fossil record for scientists to study and understand. The presence of epicontinental seas profoundly influenced the development of marine ecosystems, the dispersal of species, and the deposition of sediments. Shallow waters facilitated high productivity, complex food webs, and evolutionary experimentation, while sediment deposition preserved these ecosystems in remarkable detail. The interplay between rising seas, retreating waters, and environmental variability created a dynamic landscape that drove evolution, promoted biodiversity, and shaped the marine and terrestrial world. Fossils from these shallow seas continue to provide insights into the life, climate, and geology of the past, highlighting the importance of high seas and epicontinental waters in the history of life on Earth. The shallow epicontinental seas were environments of continual change and adaptation. Organisms living in these waters had to respond to shifts in sea level, temperature, salinity, and sedimentation. The connectivity provided by these seas allowed species to migrate, disperse, and mix with other populations, while periods of isolation promoted speciation. The abundance of resources combined with environmental pressures drove evolutionary innovation, shaping the diversity of life in ways that are still evident in the fossil record. These seas acted as crucibles of biological activity, influencing ecosystems, climate, and geological processes across continents and oceans. The shallow waters of epicontinental seas also played a role in the development of ancient coastal environments. Mangroves, tidal flats, lagoons, and estuaries formed at the margins of these seas, providing habitats for diverse organisms. These transitional zones were important for feeding, breeding, and shelter, supporting both marine and terrestrial species. Sediment deposition in these areas contributed to the formation of rich fossil beds, preserving the interactions between land and sea and providing evidence of ancient environmental conditions. The interplay between high seas, shallow waters, and marine life created a dynamic world in which life could flourish, adapt, and diversify. The expansion and retreat of epicontinental seas shaped the evolution of species, the deposition of sediments, and the chemistry of the oceans. The fossil record preserved in these sediments offers a detailed view of ancient ecosystems, revealing the complexity, diversity, and adaptability of life in shallow seas. The effects of these seas extended beyond the water itself, influencing climate, coastal environments, and the distribution of life across continents. Shallow epicontinental seas were sites of extraordinary biodiversity and ecological complexity. The combination of sunlight, warmth, nutrient availability, and habitat diversity created ideal conditions for life to thrive. Predation, competition, reproduction, and dispersal shaped communities, while environmental fluctuations encouraged adaptation and specialization. Sediments preserved fossils and trace evidence, offering a window into the past and revealing the interactions between organisms and their environment. The ebb and flow of these seas over millions of years created opportunities for evolutionary innovation and helped shape the course of marine life on Earth. The long-lasting effects of epicontinental seas are evident in both the fossil record and the geological landscape. Sedimentary rocks formed in these shallow waters preserve the remains of diverse marine life, document environmental changes, and record sea level fluctuations. The interactions between organisms, sediments, and water-shaped ecosystems influenced climate and contributed to the distribution of nutrients and minerals. These seas provided the conditions necessary for evolutionary experimentation, the spread of species, and the preservation of life for millions of years. Shallow seas and high ocean levels created dynamic habitats that fostered the growth, adaptation, and diversification of life. The interactions between water, sediments, organisms, and climate drove ecological and evolutionary processes that produced some of the most diverse and productive marine ecosystems in Earth's history. Fossils preserved in these environments provide invaluable insights into the past, showing how shallow epicontinental seas influence marine life, sediment deposition, climate, and the evolution of species. The cycle of flooding and retreating waters shaped ecological patterns and evolutionary trajectories. Organisms had to cope with changing conditions, which favoured adaptability, specialization, and diversification. The connectivity provided by epicontinental seas allowed the dispersal of species, while periods of isolation promoted speciation. Sedimentation preserved the record of these interactions, offering a detailed view of ancient ecosystems. The complex interplay between environmental change, ecological opportunity, and evolutionary pressure made epicontinental seas vital arenas of life, adaptation, and survival, leaving a legacy that continues to be studied and understood millions of years later. The world of plants during the Jurassic Era, spanning from about 199 million to 145 million years ago, was a realm dominated by greenery that might look familiar yet completely alien compared to the landscapes we know today. During this long stretch of time, the Earth was filled with dense forests, vast fern prairies, and scattered groves of cycads, with occasional glimpses of the earliest flowering plants just beginning to appear, hinting at the dramatic botanical revolutions to come. The dominant plant groups were conifers, ferns, cycads, and ginkgos, each playing a critical role in shaping the terrestrial environment, the climate, and the food webs that supported enormous reptiles, including the many species of dinosaurs that roamed the land. The world of plants was a living, breathing network of energy and nutrients, and understanding it requires diving into the life forms themselves, their distribution, and how they interacted with their surroundings. Conifers were among the most widespread and ecologically significant trees during this era. Towering above other plants, they formed extensive forests that covered much of the land, creating canopies that shaded the forest floor and influenced the microclimates beneath. These trees, which included relatives of modern pines, spruces and firs, had needle-like leaves that helped reduce water loss and allowed them to survive in a variety of climates, from tropical regions near the equator to the cooler, more temperate zones nearer the poles. Their woody structures and resin-rich tissues not only made them resistant to decay and pests, but also contributed to the fossil record, as the resin sometimes hardened into amber, preserving delicate insects and plant fragments for millions of years. Conifer forests were particularly important because they provided shelter and food for numerous herbivorous dinosaurs, who fed on their leaves, shoots, and seeds, and indirectly supported carnivorous species that preyed upon these plant eaters. The dense forests also stabilized soils and affected rainfall patterns locally, contributing to the overall climate dynamics of the Jurassic world. Ferns were another group of plants that thrived during this period, though they often occupied different ecological niches than the taller conifers. Ferns range from small, delicate understory species to enormous tree ferns, some reaching heights of more than 30 feet. They reproduce by releasing spores, which could drift on the wind and colonize moist soils, floodplains, and riverbanks. Ferns were exceptionally well suited to the humid, warm climate that characterized much of the Jurassic, and they could form thick, lush ground cover that trapped moisture, slowed erosion, and created habitats for small animals and insects. Tree ferns often grew in swampy areas and near watercourses, where their broad fronds captured sunlight and created a mosaic of light and shadow beneath. The spore-based reproduction of ferns meant they could rapidly colonize areas after disturbances such as floods, volcanic activity, or falling trees, making them resilient components of Jurassic landscapes. Ferns also left behind abundant fossilized impressions, which helped scientists reconstruct the density and diversity of the plant life of this era. Cycads, often mistaken for palms because of their stout, unbranched trunks and large, pinnate leaves, were another striking feature of Jurassic vegetation. They reproduced using cones, with separate male and female structures, and relied on wind and primitive insect pollinators to distribute their pollen. Many cycads formed dense groves, often near lakes, rivers, and seasonal wetlands, and provided both food and shelter to small dinosaurs, insects, and other animals. Their slow growth and long lifespan allowed them to persist through varying climatic conditions, though their reliance on specific habitats meant they were more restricted geographically compared to the widespread conifers and ferns. Fossilized cycads reveal intricate details of their leaves and reproductive structures, showing that they were highly adapted to the climates of the time, and their presence in various locations across the continents indicates that they were a critical part of many Jurassic ecosystems. Ginkgos, represented today by a single surviving species, Ginkgo biloba, were already well established by the Jurassic. They were relatively tall trees with fan-shaped leaves that turned yellow in autumn, though the concept of seasons in many parts of the Jurassic would have been different from today due to a generally warmer global climate. Ginkgos reproduced using seeds rather than spores, and their seeds were surrounded by fleshy coatings that may have been eaten and dispersed by animals, although this process is difficult to fully reconstruct. The leaves of ginkgos have a distinctive shape, often split into two lobes, and their tough, resilient structure allowed them to survive in a variety of environments. Fossil evidence shows that ginkgo-like trees were already widespread during this era, contributing to the complexity of forests and providing an additional layer of biodiversity in areas dominated by conifers, ferns, and cycads. Amidst these dominant groups, the very first flowering plants, or angiosperms, were beginning to emerge. Though still rare and not yet ecologically dominant, these early flowering plants represented a revolutionary shift in plant evolution. Unlike conifers, ferns, and cycads, which rely on wind or water for reproduction through spores or cones, flowering plants developed flowers to attract insects and other small animals, creating new opportunities for pollination and seed dispersal. These early angiosperms were likely small, herbaceous plants, growing in the understory of forests or along edges of rivers and lakes, and their tiny flowers would have been adapted to the limited pollinators available at the time. Fossilized pollen grains and fragments of leaves suggest that flowering plants first appeared during the later part of the Jurassic, setting the stage for the explosive diversification that would occur in the Cretaceous, when they would become the dominant group of plants across the globe. The interactions between these different plant groups were complex and shaped the landscapes in profound ways. Conifer forests created shaded understories that allowed ferns and early flowering plants to thrive, while cycads and ginkgos occupied niches in areas with slightly different soil moisture and sunlight conditions. The variety of leaf shapes, sizes, and reproductive strategies helped maintain biodiversity and ensured that some plants could survive even during periods of climatic stress. Forests were not uniform, but rather mosaics of different plant types, with layers of vegetation ranging from towering conifers to intermediate cycads and ginkgos, down to ferns and small flowering plants near the ground. This vertical stratification created habitats for a wide array of organisms, including insects, small vertebrates, and the massive dinosaurs that would graze, browse, or hunt among the trees. Soil composition during the Jurassic was also influenced by this abundant plant life. Leaf litter from conifers, ferns, cycads, and ginkgos accumulated on the forest floor, decomposing slowly due to the climate and contributing to the formation of nutrient-rich soils. In swampy areas, thick layers of plant material could form peat-like deposits, which over millions of years could be transformed into coal, capturing snapshots of Jurassic vegetation. The cycling of nutrients through decay and growth supported the continuous regeneration of forests, allowing dense plant communities to persist for millions of years in some regions. In addition, the extensive root systems of trees and cycads helped stabilize the soil, reducing erosion and enabling the formation of rivers, floodplains, and lakes with relatively clear waters that were important for both plants and animals. The distribution of plant life was influenced by latitude and climate. Near the equator, lush, dense conifer forests and extensive fern thickets dominated, creating warm, humid, and often swampy environments. Moving towards the poles, forests became less dense, and conifers, ginkgos, and cycads adapted to slightly cooler and more seasonal conditions. Paleobotanical evidence shows that some conifers were capable of surviving near polar regions, where for long periods of the year there would have been extended darkness or continuous daylight. These adaptations demonstrate the resilience and versatility of Jurassic plants, which had to cope with a variety of environmental challenges while continuing to sustain complex ecosystems. Rivers, lakes, and other freshwater systems were critical for the spread and growth of plant life. Ferns, cycads, and the earliest flowering plants often grew along riverbanks and lake margins, where soil was moist and nutrients were abundant. Seasonal flooding could disperse spores, seeds, and vegetative fragments, allowing plants to colonize new areas rapidly. Wetlands supported dense growths of ferns and cycads, while conifers thrived slightly further from the water in well-drained soils. These water-rich environments also provided habitats for early amphibians, insects, and small reptiles, creating an intricate web of life that connected aquatic and terrestrial ecosystems. Fire may have played a role in shaping some plant communities, particularly in drier regions or during periods of prolonged drought. Conifers, with their thick bark and resin-rich tissues, could survive occasional fires, while ferns and cycads could quickly recolonize burned areas from spores or vegetative fragments. Fire would have opened up forest gaps, allowing sunlight to reach the understory and giving early flowering plants an opportunity to expand. This dynamic of disturbance and regeneration contributed to the diversity and resilience of Jurassic vegetation, ensuring that no single plant type could dominate every habitat indefinitely. The interplay between plants and animals was another defining feature of Jurassic ecosystems. Large herbivorous dinosaurs such as sauropods were particularly dependent on the abundant foliage provided by conifers, cycads, and ferns. Their feeding habits, which involved stripping leaves from trees or consuming whole plants, influenced plant distribution and growth patterns. Some plants may have evolved tougher leaves, spines, or chemical defenses in response to browsing pressure, while others benefited from herbivores dispersing seeds or creating openings for new growth. Smaller animals, including insects, early mammals and reptiles, interacted with ferns, cycads, ginkgos and flowering plants in similar ways, feeding on leaves, seeds, or reproductive structures, and aiding in pollination and seed dispersal. Fossil evidence provides a remarkable window into this world of Jurassic vegetation. Petrified wood, leaf impressions, cones, pollen grains, and even amber with preserved plant material offer detailed glimpses into the diversity, structure, and function of plant communities. In many locations, fossilized forests are preserved in remarkable detail, showing the arrangement of trees, undergrowth, and watercourses. These fossils allow scientists to reconstruct ancient climates, understand the evolutionary pathways of major plant groups, and trace the origins of flowering plants, which would come to dominate much of the Earth's flora millions of years later. By the end of the Jurassic, the foundations for future plant evolution were being laid. Conifers remained dominant, ferns continued to thrive, cycads and ginkgos were widespread, and the first flowering plants were emerging as a small but significant part of the flora. These plant groups interacted with one another and with the broader ecosystem in ways that set the stage for the dramatic changes of the Cretaceous, when flowering plants would rise to prominence and transform terrestrial landscapes across the globe. The dense forests, wet lowlands, riverbanks, and diverse plant communities of the Jurassic represent a critical chapter in the history of life on Earth, illustrating the intricate relationships between plants, climate, geography, and animal life over tens of millions of years. This detailed understanding of Jurassic vegetation reveals the complexity and richness of plant life during a period when the Earth was warmer, seas were higher, and continents were arranged differently than today. The dominance of conifers, the lush presence of ferns, the distinctive groves of cycads, the resilient ginkgos, and the first flowering plants all contributed to shaping ecosystems that would support a remarkable variety of life, influencing evolutionary pathways, climate dynamics, and the very structure of terrestrial habitats for millions of years to come. The record left by these plants, from fossilized leaves and wood to pollen and amber, continues to inform our understanding of how life adapted to different conditions, how ecosystems functioned in the deep past, and how early plant groups set the stage for the flowering plants that dominate much of our world today. Each tree, fern, and cycad contributed to the cycles of energy and nutrients, supported countless animals, and interacted with the climate and soils to create the lush and varied landscapes that characterized the Jurassic Era. The slow, persistent growth of forests, the rapid spread of ferns after disturbances, the stable presence of cycads and ginkgos, and the cautious emergence of flowering plants combined to create a complex and resilient tapestry of plant life, one that shaped the very face of the Earth during this fascinating chapter in natural history. The ongoing study of Jurassic vegetation provides insights not only into the past, but also into the principles of ecological balance, adaptation, and evolution. By examining the dominance of conifers, the abundance of ferns, the survival strategies of cycads and ginkgos, and the first tentative steps of flowering plants, scientists can better understand how plants respond to changing climates, how they interact with other organisms, and how ecosystems evolve over tens of millions of years. The Jurassic Era, with its towering forests, sprawling fernlands, and early flowers, stands as a vivid illustration of life's ability to adapt, diversify, and create enduring landscapes that would influence the course of evolution for millions of years thereafter. The vegetative patterns of the Jurassic were shaped not only by climate and geography, but also by geological processes. The breakup of the supercontinent Pangaea during this time created new coastlines, mountain ranges, and basins, altering rainfall patterns, soil composition, and the availability of light and water. In these newly formed environments, conifers often dominated upland areas, ferns flourished in valleys and floodplains, cycads and ginkgos occupied specific ecological niches, and flowering plants began to exploit unoccupied spaces. Rivers, lakes, and coastal wetlands acted as conduits for plant migration, allowing spores and seeds to travel long distances and colonize new areas, while volcanic activity periodically reshaped landscapes and created fresh substrates for plants to inhabit. The Jurassic vegetation was thus not static but a dynamic and evolving system, responding to shifts in climate, tectonics, and ecological pressures. Each plant group played a unique role: conifers as the tall structural backbone of forests, ferns as opportunistic colonizers of disturbed and moist areas, cycads and ginkgos as long-lived survivors of varied habitats, and flowering plants as the pioneering innovators setting the stage for future botanical revolutions. Their combined presence formed the intricate fabric of Jurassic ecosystems, influencing everything from herbivore behavior to soil formation and atmospheric composition, and leaving behind a rich legacy preserved in the fossil record for scientists to uncover hundreds of millions of years later. The Jurassic world of plants was thus a complex, interconnected system, with forests, wetlands, riverbanks, and open areas each supporting specific plant communities that interacted with one another in subtle and profound ways. The towering conifers, expansive ferns, enigmatic cycads, resilient ginkgos, and the earliest flowering plants together created a landscape of diversity and resilience, demonstrating the adaptability of life and the continuous interplay between organisms and their environment. This lush vegetation was more than just scenery. It was a living framework supporting vast ecosystems, shaping climates, soils, and habitats, and setting in motion evolutionary processes that would influence life on Earth for hundreds of millions of years after the last Jurassic conifer had fallen and the first flowering plants had begun their global conquest. The fossil record shows that conifers were not only widespread but incredibly diverse, with different species adapting to a variety of climates and soil types. Some thrived in the warm, wet lowlands, while others could tolerate drier uplands. Ferns, meanwhile, exhibited remarkable plasticity, from small, shade-tolerant species to towering tree ferns in swamps and floodplains. Cycads and ginkgos, though slower growing, offered structural diversity and stability in the landscape. Flowering plants, though still minor players, began experimenting with shapes, colours, and reproductive strategies that would eventually lead to the vast floral diversity we see today. Each plant group occupied a slightly different ecological niche, minimizing competition while maximizing the use of available resources. This vegetation shaped not just terrestrial ecosystems, but also influenced the atmosphere and climate. Dense forests of conifers, for instance, contributed to carbon sequestration, while the evaporation from leaves and transpiration affected humidity and precipitation patterns. The accumulation of plant material on the forest floor influenced soil formation and nutrient cycles, while the presence of ferns and cycads in wetlands helped maintain water quality and soil stability. These interactions between plants, climate, and landscape created feedback loops that supported the growth and resilience of Jurassic ecosystems. Even within conifer forests there was variation. Some species produced large, fleshy cones that could be eaten by herbivores, while others released smaller, wind-dispersed seeds. The structure of the canopy influenced the amount of light reaching the understory, allowing shade-tolerant plants like ferns and early flowering species to establish themselves. Cycads and ginkgos often occupied open areas or forest edges, where sunlight was plentiful and competition with towering conifers was reduced. This vertical and horizontal partitioning of space enabled high levels of biodiversity, with multiple plant species coexisting in the same region without directly outcompeting one another. Over millions of years, these plant communities experienced cycles of expansion, migration, and extinction, driven by changing climates, volcanic activity, and the shifting continents. Fossil evidence indicates that some conifer forests persisted for tens of millions of years in particular regions, while ferns and cycads rapidly colonized new habitats created by rivers, floods, or volcanic eruptions. Early flowering plants were slow to spread initially, but laid the genetic groundwork for the explosive diversification that would occur in the following Cretaceous period. The ongoing interplay between plant groups, environmental conditions, and animal interactions created a dynamic and evolving landscape that was both resilient and adaptable, capable of supporting the enormous and varied fauna of the Jurassic world. By the late Jurassic, the stage was set for a botanical revolution. Flowering plants, still minor in abundance, were beginning to experiment with new forms, reproductive strategies, and interactions with animals. Their appearance marked the start of a transformation that would eventually reshape terrestrial ecosystems, allowing angiosperms to dominate vast regions and outcompete many of the older gymnosperm groups. Meanwhile, conifers, ferns, cycads, and ginkgos continued to play critical roles, forming the backbone of Jurassic landscapes and providing resources and habitats for countless species of dinosaurs, insects, and other animals. The interplay between these plants and the environment highlights the complexity, adaptability, and resilience of life during this period, offering a detailed view of a world where greenery was not just a backdrop but a driving force in the evolution of ecosystems. Vegetation during the Jurassic was also influenced by regional variations in rainfall, temperature, and soil fertility. In areas with abundant rainfall, such as lowland floodplains and near coastlines, conifers formed dense forests, often interspersed with ferns and cycads that took advantage of wetter soils. In drier upland areas, conifers adapted to conserve water with needle-like leaves, while cycads and ginkgos maintained their presence through long lifespans and slow growth. Early flowering plants may have favoured riverbanks and forest edges, where water and light availability supported their growth. These microhabitats created pockets of diversity within broader vegetative zones, allowing multiple plant groups to coexist and interact. Fossilised pollen and spores provide clues about plant diversity and abundance. Conifers dominated pollen records in many regions, reflecting their widespread presence, while fern spores were particularly abundant in wetland and lowland deposits. Cycads and ginkgos appeared more sporadically, reflecting their more specialised ecological niches. Early flowering plants are identified primarily through minute pollen grains, indicating their presence even when they were not yet dominant. Over the course of the Jurassic Era, a time stretching from roughly 199 million years ago to 145 million years ago, life on Earth was undergoing remarkable changes, not only among the giant reptiles that tend to capture the popular imagination, but also among smaller, often overlooked creatures whose presence and activity shaped the very fabric of ecosystems. Among these smaller creatures, insects and early arthropods were of immense importance. These creatures, ranging from delicate winged insects to sturdy armoured beetle-like forms, were far from mere background inhabitants of the ancient world. They were busy, active, and vital components of the forests, swamps, riverbanks, and coastal areas of the Jurassic landscape, playing roles that range from pollination to decomposition, predation, and even acting as prey for larger animals. The insects of this era were diverse in form and function, though they retained many primitive features inherited from their ancestors that had first begun to colonize the land during the late Paleozoic era. While today we might take for granted the wide variety of insect forms, during the Jurassic the groundwork was being laid for much of the diversity we see in modern insect life. During the early part of the Jurassic, many of the insect groups that had emerged during the late Triassic period continued to flourish and diversify. Among the earliest and most prominent of these were members of the order Odonata, the dragonflies and damselflies. These were not small, delicate creatures like some of their modern relatives. Some species had wingspans that stretched to nearly 70 centimetres, making them formidable predators in the skies above the forests, lakes, and wetlands. They patrolled the waters and air with sharp mandibles and keen eyesight, hunting smaller insects with remarkable precision. These early aerial hunters contributed to maintaining a balance in insect populations, feeding on mosquitoes, midges, and other tiny creatures, ensuring that no single species became overly dominant. Dragonflies and damselflies also played a role in the food chain, as they themselves became prey for small vertebrates, including early birds, small pterosaurs, and amphibians. In this way, they connected aquatic and terrestrial ecosystems, starting life in water as nymphs and moving to the air as adults, linking different parts of the Jurassic environment in a complex web of life. Other groups of insects that thrived during the Jurassic included the early beetles, or Coleoptera. These beetles were diverse in shape and size, with some forming elongated, almost cylindrical bodies adapted for life among the bark and leaves of coniferous trees, while others were flatter, moving among the soil and detritus on the forest floor. They had strong mandibles, capable of cutting through plant material, wood, or even the exoskeletons of other arthropods. Beetles contributed greatly to the breakdown of plant material, acting as natural recyclers, breaking down dead wood, fallen leaves, and other organic matter, and returning nutrients to the soil. By doing so, they supported the lush vegetation of the Jurassic forests, which were dominated by towering conifers, ferns, and cycads. Some beetles even began to explore niches involving feeding on pollen or seeds, although this would become more pronounced later as flowering plants began to emerge toward the end of the Jurassic. Beetles of this time were also preyed upon by small reptiles, amphibians, and other arthropods, making them a vital link in terrestrial food chains. True flies, or members of the order Diptera, also existed in primitive forms during the Jurassic, although they were less diverse than they would become in later eras. These early flies were primarily small, with 2 functional wings and specialized mouthparts adapted to piercing, sucking, or sponging liquids. They likely played important roles in scavenging fluids from plants, fungi, and animal carcasses, helping to speed decomposition and recycling nutrients. In the wet, swampy environments that were common in many regions, these flies may have been abundant, buzzing around stagnant pools, decaying plant matter, and damp forest floors. Even small numbers of these flies would have provided significant food sources for insectivorous vertebrates, such as small lizards, early mammals, and pterosaurs, creating yet another layer of ecological interaction. Another remarkable group of Jurassic insects were the orthopterans, which included grasshopper-like and cricket-like forms. These insects were largely herbivorous, feeding on the abundant ferns, cycads, and conifer needles. With strong hind legs adapted for jumping, they could quickly escape predators or move from plant to plant, feeding on foliage and contributing to the cycling of plant matter in forests and open plains. The sounds of these insects created by stridulation, the rubbing together of specialized body parts, may have been among the first rhythmic noises of terrestrial landscapes, filling the Jurassic air with background chirps and buzzes. Their presence would have been essential not only for their own survival, but also for the animals that depended on them for food, such as early mammals and small theropod dinosaurs that hunted insects and other small creatures. Mantises, or their early relatives, may also have existed in primitive forms during the Jurassic. These insects were predators, often ambushing smaller arthropods with spiny, grasping forelegs and a keen sense of sight. By controlling populations of smaller insects, they helped maintain the balance of Jurassic ecosystems. Some of the earliest cockroach-like insects belonging to the order Blattodea were also abundant. These insects were generalist feeders, consuming plant debris, fungi, and decaying matter, and they were highly adaptable, inhabiting forests, riverbanks, and even caves. Cockroaches played an essential role in decomposition and nutrient cycling, ensuring that the thick layers of fallen plant material did not accumulate excessively in the dense Jurassic forests. One of the most fascinating aspects of Jurassic insect life was the gradual interaction with early flowering plants, or angiosperms, which began to appear toward the later part of the era, although they were still relatively rare and local. Certain insects began exploring these new sources of food, feeding on pollen, nectar, or seeds, and in doing so they inadvertently started the earliest forms of pollination, a mutualistic relationship that would dramatically shape plant evolution in the following eras. This development marked the beginning of a new ecological connection, linking the survival and reproduction of plants directly to the behavior and movement of insects. Insects that could navigate flowers, collect pollen, or feed on nectar gained new opportunities for nutrition, while plants that could attract insects increased their chances of successful reproduction. This early coevolution, although in its infancy during the Jurassic, set the stage for the dramatic flowering plant-insect relationships that dominate modern terrestrial ecosystems. Spiders and other arachnids were also significant during this period, though they are not insects but close arthropod relatives. Spiders became effective predators, weaving webs or hunting actively on forest floors and among foliage. Their presence controlled the populations of smaller insects, contributing to the overall balance of the ecosystems. Mites and other tiny arachnids thrived in soil, leaf litter, and on plant surfaces, feeding on decaying organic matter, fungi, and microscopic organisms. Even small arthropods like millipedes and centipedes were abundant, with millipedes acting as decomposers, feeding on dead plant material, and centipedes functioning as predators, hunting insects and other arthropods. The diversity of Jurassic insects was further increased by the presence of large winged relatives of modern mayflies, stoneflies, and caddisflies. These insects were intimately connected with aquatic habitats, laying eggs in streams, rivers, lakes, and swampy areas. The aquatic nymphs of these species were highly adapted to water life, feeding on algae, detritus, or smaller aquatic invertebrates, while adults emerged to reproduce and disperse, linking aquatic and terrestrial ecosystems. Their life cycles ensured that nutrients moved from water to land and back again, reinforcing the complex connections among the plants, animals, and microorganisms of the time. Mayflies, with their short adult lives, may have been particularly abundant in riparian zones, forming massive swarms that provided food for emerging amphibians, small reptiles, and even early birds and pterosaurs. The Jurassic Era also saw the continued dominance of primitive winged insects that resembled modern lacewings and antlion-like species. These predators and scavengers played crucial roles in regulating populations of smaller arthropods and maintaining ecological balance. The presence of these insects also encouraged the evolution of defensive adaptations among their prey, such as protective exoskeletons, camouflage, and behavioral strategies to escape predation. This predator-prey dynamic fostered evolutionary innovation and shaped the behaviors, forms, and survival strategies of both insects and their predators. In many Jurassic environments, the sheer abundance of insects and early arthropods created vast microhabitats and ecological niches. Leaf surfaces hosted an array of tiny herbivores and their predators. Decaying logs and soil contained beetles, ants, and cockroach-like insects, and the air was filled with flying predators and pollinators. Swamps and wetlands teemed with aquatic larvae, while forest canopies offered new challenges and opportunities for flight-capable insects. Insects not only occupied these niches but actively shaped them. Feeding patterns influenced plant growth, burrowing and tunneling altered soil and leaf litter structure, and swarming behaviors could influence the behavior of larger animals, from small mammals to juvenile dinosaurs. They were architects of their own ecological world, creating networks of interaction that extended far beyond their tiny size. Social insects, though less diverse and complex than they would become in the Cretaceous and modern eras, may have begun rudimentary communal behaviours. Some cockroach-like species possibly formed aggregations in response to food availability or environmental stress, while certain primitive ant-like insects may have exhibited simple cooperation. These early social behaviours laid the foundation for more complex insect societies that would later dominate ecosystems. The emergence of such behaviours, combined with flight, predation, herbivory, scavenging, and pollination, ensured that insects were deeply integrated into the structure of Jurassic ecosystems. They were not simply inhabitants, but active participants shaping evolutionary pathways for plants, vertebrates, and other invertebrates alike. Insects also played indirect roles in supporting vertebrate life. Small dinosaurs, early mammals, amphibians, and reptiles often relied on insects for sustenance, particularly when plant material or larger prey was scarce. Juvenile dinosaurs, for example, may have depended heavily on insects and other small arthropods during their early growth stages, while small mammals, which were primarily insectivorous at this time, were shaped in part by the abundance, diversity, and nutritional availability of insects. Even larger carnivorous dinosaurs may have occasionally supplemented their diets with insects or larvae, especially when easier prey was unavailable, showing that insects had pervasive influence across multiple trophic levels. Throughout the Jurassic Era, the roles of insects and early arthropods extended beyond the immediate ecosystem to influence evolutionary pressures. Their feeding habits drove plant defenses, including tougher leaves, spines, and chemical compounds, which in turn influenced the types of herbivores that could survive. Predatory insects and arachnids created pressures on other arthropods to evolve better camouflage, speed, or protective armor. Even the smallest insects, by laying eggs in water or soil, impacted sediment composition, nutrient distribution, and the structure of aquatic and terrestrial habitats. Over millions of years, these small creatures, often invisible to casual observers, had cumulative effects that helped shape the Jurassic world in ways comparable to the larger, more famous dinosaurs and pterosaurs. Among the remarkable features of Jurassic insects was the emergence of highly specialized mouthparts adapted to specific diets. Some beetles developed mandibles for chewing hard seeds or wood. Some flies evolved piercing structures for feeding on plant juices or animal fluids, and some primitive butterflies or moth-like insects may have begun exploring nectar from emerging flowering plants. This specialization allowed multiple insect species to coexist in the same environment without directly competing for the exact same resources, increasing overall biodiversity. By exploiting different food sources, insects promoted the spread and diversification of plants, while also encouraging the development of specialized predators and parasites that fed on them. In this way, Jurassic insects were at the center of a growing network of ecological interactions, linking plants, predators, prey, and decomposers in a dynamic system that would continue to evolve for millions of years. Throughout the Jurassic Era, the fossil record indicates that insects were extraordinarily diverse, with multiple families and orders represented across different regions. Fossils of dragonflies, beetles, flies, cockroaches, orthopterans, and aquatic nymphs have been found in areas that were once lush forests, river floodplains and coastal wetlands. Amber, although less common in Jurassic deposits than in later periods, has preserved some insects in remarkable detail, showing wing venation, body segmentation, and even mouthparts, providing evidence of the intricate adaptations that had evolved over millions of years. Fossilized tracks, burrows, and feeding traces also reveal the widespread activity of insects, from surface grazing on leaves to tunneling into decaying wood, demonstrating that insects were integral components of the environment rather than occasional visitors. The interactions between insects and other animals during the Jurassic era were highly complex. Insects were hunted by amphibians, reptiles, early birds, small mammals, and even other insects. In turn, they fed on plants, fungi, detritus, and smaller arthropods. This constant exchange of energy and nutrients created stable, interconnected ecosystems capable of supporting large, diverse populations of plants and animals. Insects helped maintain soil fertility, control plant populations, disperse seeds, and regulate populations of other arthropods, illustrating that the survival and success of larger organisms depended in subtle but essential ways on these tiny creatures. Insects and early arthropods also played a role in shaping the very structure of the Jurassic landscape. By feeding on leaves, boring into wood, or tunneling into soil, they influenced plant architecture, forest density, and decomposition rates. Their burrows aerated soil, enabling roots to penetrate more deeply and water to percolate more effectively. By cycling nutrients from dead material back into the ecosystem, insects contributed to the extraordinary productivity of Jurassic forest swamps and wetlands. Areas rich in insect activity would have supported denser vegetation and a wider variety of animals, creating hotspots of biodiversity. Over millions of years, the continued interaction between insects and the environment created feedback loops, where the presence of abundant plant life encouraged more insect life, which in turn supported more plant growth and more animal diversity, forming intricate and resilient ecosystems. The role of insects in the Jurassic era was not limited to food webs and plant interactions. Some species may have assisted in dispersing microorganisms, fungi, or even spores of early plants. By moving across the landscape, insects could transport tiny particles from one location to another, contributing to the spread of life forms that were otherwise immobile. Their ability to move rapidly and in large numbers made them effective agents of ecological connectivity, linking distant habitats and promoting genetic diversity among plants, fungi, and other small organisms. The spread of pollen by early flower-visiting insects, though still in its infancy, exemplifies the potential influence that even small creatures could exert over the evolution of entire lineages of life. Predation pressures exerted by insects were also critical in shaping evolutionary strategies among other arthropods. Defensive adaptations such as hardened exoskeletons, camouflage, spines, toxic secretions, and flight evolved in response to insect predators and competitors. In turn, predatory insects developed ever more precise hunting strategies, sharper mandibles, swifter flight, and keen sensory organs, driving an ongoing arms race in miniature. These interactions, often invisible to human observers, were fundamental in shaping the diversity and specialization of Jurassic arthropods, highlighting the dynamic nature of evolutionary pressures during this period. By the late Jurassic, the stage was set for a dramatic increase in both insect diversity and ecological complexity. The emergence of flowering plants, the continued expansion of coniferous forests, the development of wetlands and rivers, and the fragmentation of continents all created new niches for insects and arthropods to exploit. Insects were increasingly involved in pollination, seed dispersal, and the cycling of nutrients, while continuing to serve as essential food for vertebrates and other arthropods. The cumulative effect of millions of years of evolution during the Jurassic era produced a rich and dynamic insect fauna that was crucial for the functioning of terrestrial ecosystems, establishing patterns and relationships that would continue to shape the Earth's biosphere into the Cretaceous and beyond. Throughout this era, insects were neither passive observers nor mere background elements in the grand tapestry of life. They were dynamic, diverse, and active participants in every ecological system they touched. Their evolution, behavior, and interactions influenced the shape of plant communities, the survival strategies of other animals, and the structure of ecosystems as a whole. from the dragonflies with massive wings patrolling Jurassic skies, to the beetles burrowing into decaying logs, to the primitive pollinators visiting the earliest flowers, insects and early arthropods were fundamental in maintaining the balance, productivity, and complexity of the Jurassic world. Over the span of millions of years, these small creatures quietly but profoundly contributed to shaping a living planet, demonstrating that even the tiniest organisms can have an enormous impact on life and the environment. Insects and early arthropods, by their sheer numbers, diversity and variety of roles, exemplified the intricate interdependence that characterized Jurassic ecosystems. They were prey and predator, scavenger and decomposer, pollinator and herbivore, each function influencing countless others. Their lives, often measured in days, months or years, connected to longer-lived plants, reptiles and vertebrates in a constantly shifting network of interactions. The success of these small creatures was both a product of the era's environmental richness and a driver of further evolutionary change, making them indispensable architects of the Jurassic world. Even as continents drifted, climates warmed, and new ecological niches appeared, insects adapted, diversified, and maintained their central role in Jurassic ecosystems. Their behaviours, feeding strategies, reproductive cycles, and interactions with plants and animals set the stage for further diversification in the Cretaceous, particularly with the rise of flowering plants and the proliferation of pollinator-insect relationships. By understanding the roles of Jurassic insects and early arthropods, one can appreciate the subtle but profound ways in which these small creatures shaped ecosystems, influenced the evolution of other species, and contributed to the complexity and richness of life on Earth during this remarkable geological period. Insects were more than just small animals moving among plants and soil. They were essential cogs in the machinery of Jurassic life, connecting water and land, plants and predators, decomposers and nutrient cycles, ensuring that ecosystems functioned smoothly. The variety of forms, from giant predatory dragonflies to minute detritivorous mites, demonstrated the adaptive flexibility of arthropods and hinted at the explosive diversification that would follow in later periods. Even today, the study of these ancient insects provides insight into the evolutionary pressures, ecological interactions, and environmental conditions of the Jurassic era, revealing a world that was complex, interconnected, and shaped in no small part by the tiniest creatures alive at that time. The presence of insects and early arthropods in virtually every Jurassic habitat, from forest canopies to swampy wetlands, from riverbanks to coastal dunes, underscores their ecological significance. They fed on plants, other insects, fungi and decaying matter, while providing nutrition for countless vertebrates and invertebrates. They influenced plant morphology, soil structure, nutrient cycling, and even the behaviour of larger animals. They were both a product of their environments and agents of change, shaping the evolutionary trajectory of life on Earth. Over the span of millions of years, these creatures, often overlooked due to their size, were indispensable participants in the dynamic, evolving and intricate ecosystems of the Jurassic era. Freshwater ecosystems during the Jurassic period were vibrant, dynamic, and critical habitats that supported a wide variety of life forms, including fish, amphibians, and the earliest turtles. Rivers, lakes, and lagoons were the main types of freshwater habitats, each with its own unique characteristics and ecological roles. These waters not only provided a home for aquatic organisms, but also played an essential role in shaping the surrounding landscapes, influencing the climate and supporting terrestrial animals that depended on fresh water for survival. Rivers during the Jurassic period often flowed from higher inland areas toward the shallow seas and oceans, carving valleys and floodplains as they moved. These rivers could be broad and slow-moving, forming wide channels with gentle currents, or they could be narrow and swift, cutting deep into the terrain and carrying sand, silt, and organic debris along their paths. The constant flow of water in rivers created habitats with a mix of shallow areas, deeper pools, and bends where eddies and slower currents formed. These varying conditions allowed a diverse array of fish species to thrive, from small agile swimmers to larger predators adapted to hunting in flowing water. Some rivers were lined with dense vegetation, including ferns, horsetails, and conifers, whose roots helped stabilize the banks and whose fallen leaves and branches provided food and shelter for aquatic life. The fish in Jurassic rivers were diverse and highly adapted to their environments. Many were early ray-finned fish, which had lightweight skeletons and flexible fins that allowed them to maneuver easily in currents. Some were armoured with bony plates, offering protection against predators, while others were streamlined and fast, capable of chasing smaller fish or insects that fell into the water. Fossil evidence shows that rivers supported both herbivorous and carnivorous fish, each playing a role in the ecosystem by controlling algae growth, feeding on insects, or preying on smaller fish. Amphibians were also abundant in and around rivers. Early salamander-like creatures, frogs, and other amphibious species depended on the water for reproduction, laying eggs that developed into larvae or tadpoles before maturing into adults. These amphibians were both predators and prey, feeding on insects, small invertebrates, and plant material while providing nourishment for larger reptiles, early mammals, and fish. Lakes during the Jurassic period offered a different kind of freshwater environment. Many lakes were relatively calm compared to rivers, with limited currents and a more stable water level. They could be shallow, allowing sunlight to reach the bottom and support underwater plants and algae, or deeper, creating cooler, darker areas that served as refuges for certain fish and amphibians. Lake ecosystems were often complex, with distinct zones based on depth and light availability. Shallow margins were rich in vegetation, attracting amphibians and providing nesting areas for turtles. Deeper waters housed larger fish and other aquatic animals that preferred cooler and more oxygen-rich environments. Lakes could also serve as stopover points for animals moving between habitats, providing water and food for terrestrial creatures, including dinosaurs, early mammals, and flying reptiles that hunted near the shorelines. Fish in Jurassic lakes were particularly varied. Some species specialized in feeding on plankton and small invertebrates, while others were equipped with strong jaws and sharp teeth for hunting smaller fish or scavenging. Many fish had adaptations for navigating still waters, such as fins suited for precise movements and tails capable of generating bursts of speed when escaping predators. Amphibians in lakes took advantage of abundant food and shelter, often congregating in shallow waters to breed and feed. Early turtles were also prominent in lake environments. These turtles had shells for protection and limbs adapted for swimming, allowing them to navigate through aquatic vegetation and open water with ease. They fed on plants, small invertebrates, and fish, contributing to the balance of the lake ecosystem. Lagoons represented another important type of freshwater habitat during the Jurassic period. Lagoons were typically shallow, sheltered bodies of water that were separated from larger rivers or seas by natural barriers such as sandbanks, vegetation, or rock formations. These environments were often warm and nutrient-rich, making them ideal breeding grounds for fish, amphibians, and early turtles. Lagoons could experience variations in water level, temperature, and salinity, which influenced the types of organisms that could survive there. Some lagoons were connected to rivers or coastal areas, allowing species to migrate between habitats, while others were more isolated, supporting unique communities adapted to specific conditions. The fish inhabiting Jurassic lagoons often displayed a mix of traits found in both river and lake species. They could tolerate slower-moving waters like lakes, while also surviving occasional changes in water conditions such as temporary flooding or drying. Lagoons were especially important for the life cycles of amphibians. Many amphibians laid eggs in these protected waters, where larvae could grow with reduced risk from large predators. Shallow lagoon margins provided abundant vegetation, offering shelter and feeding opportunities. Early turtles also thrived in lagoons, taking advantage of soft sediment for nesting and abundant aquatic plants and small animals for food. Their presence in lagoons helped control populations of invertebrates and small fish, maintaining ecological balance. The interaction between freshwater ecosystems and the surrounding landscapes was crucial during the Jurassic period. Rivers, lakes, and lagoons influenced sediment deposition, nutrient distribution, and the formation of floodplains and deltas. These areas were often lush with vegetation, providing food and shelter for both aquatic and terrestrial organisms. Fish, amphibians, and turtles not only depended on freshwater habitats, but also played key roles in shaping them. For example, the movement of fish and amphibians helped disperse plant seeds and invertebrate eggs, contributing to the diversity and productivity of the ecosystems. Turtles, through their feeding and nesting behaviors, also impacted vegetation patterns and sediment distribution. Freshwater ecosystems were connected to other habitats, creating a network of life that extended across rivers, lakes, lagoons, and surrounding forests and plains. Many amphibians and turtles had life cycles that required access to both water and land. Juvenile amphibians might start life in water before moving to land, while adult turtles could feed in lakes but nest on riverbanks or lagoon shores. Predatory fish and amphibians influenced the behavior of smaller species, creating a web of interactions that maintained population balance. In turn, the presence of these aquatic organisms affected larger predators, including reptiles and early mammals, which relied on freshwater habitats for food and hydration. Climate and environmental conditions during the Jurassic period further shaped freshwater ecosystems. Generally warm and humid conditions with occasional dry periods affected water levels, temperature, and the availability of nutrients. Rivers could swell during heavy rainfall, creating new channels or floodplains, while lakes and lagoons could experience seasonal fluctuations in water depth. These changes influenced the life cycles of fish, amphibians, and turtles, requiring adaptability and resilience. Species that could tolerate changes in water quality, temperature, and habitat availability were more likely to thrive and reproduce successfully. The evolutionary significance of freshwater ecosystems during the Jurassic period was immense. Rivers, lakes, and lagoons provided opportunities for adaptation and diversification, allowing fish, amphibians, and turtles to develop specialized traits. Fish evolved a variety of feeding strategies, body shapes, and defensive mechanisms. Amphibians experimented with different reproductive strategies and habitat preferences. Early turtles developed protective shells, efficient swimming limbs, and versatile diets. These adaptations laid the groundwork for future evolutionary success, influencing the development of modern freshwater species millions of years later. Interactions within freshwater ecosystems were complex and multifaceted. Fish might feed on insects that fell into the water or graze on algae, while amphibians preyed on small invertebrates and were hunted by larger predators. Turtles fed on plants, insects, and small fish, but they also contributed to sediment mixing and nutrient cycling. These ecosystems were not static. They changed with seasonal variations, geological events, and shifts in climate. Floods, droughts, and sediment deposition altered habitats, creating new niches and challenging species to adapt. Over time, these pressures encouraged diversity, resilience, and specialization among aquatic organisms. The presence of plants along freshwater ecosystems added layers of complexity to Jurassic rivers, lakes, and lagoons. Ferns, cycads, horsetails, and early conifers often grew along riverbanks and lake shores, stabilizing soil and providing shade and shelter. Fallen plant material entered the water, serving as food for detritivores and creating microhabitats for larvae and small fish. Aquatic plants, such as algae and submerged ferns, offered shelter and feeding grounds, supporting juvenile fish, amphibians, and turtles. These plant-animal interactions enhanced the productivity of freshwater habitats, allowing them to sustain rich and varied communities. Freshwater ecosystems also acted as corridors for migration and dispersal. Fish could move along rivers to reach lakes or lagoons, while amphibians travelled between water bodies to breed or find food. Early turtles used waterways to travel, sometimes covering considerable distances in search of suitable feeding or nesting sites. These movements helped maintain genetic diversity, spread species across regions, and connect isolated populations. Waterways were therefore not just habitats, but also vital pathways linking ecosystems and enabling dynamic ecological processes. Predation and competition in freshwater ecosystems shaped behavior, morphology, and population dynamics. Predatory fish influenced the distribution of smaller species, while amphibians and turtles competed for food and shelter. In turn, larger reptiles and early mammals that frequented rivers, lakes, and lagoons added pressure on aquatic populations. These interactions drove evolutionary change, encouraging species to develop defenses such as shells, camouflage, speed, or the ability to burrow or hide. Competition for resources ensured that only the most adaptable or specialized species could thrive in specific microhabitats. The sediment and geology of freshwater ecosystems left lasting traces of life during the Jurassic period. Floodplains, riverbeds, lake bottoms, and lagoon sediments preserved fossils of fish, amphibians, turtles, and plant material. These fossil records provide crucial insights into the diversity, adaptations, and ecological roles of organisms that inhabited freshwater habitats. The layering of sediments over time also tells a story of environmental changes, including river meandering, lake expansion or contraction, and lagoon isolation, offering glimpses into the dynamic nature of Jurassic freshwater landscapes. Water chemistry played an essential role in determining the health and composition of freshwater ecosystems. Oxygen levels, temperature, mineral content, and pH influenced which species could survive in particular habitats. Some fish were tolerant of low oxygen levels in stagnant waters, while others required fast-flowing oxygen-rich conditions. Amphibians generally needed well-oxygenated, clean water for successful reproduction, while turtles could tolerate a wider range of conditions. Nutrients from decaying plants and organic matter fueled the growth of algae and aquatic plants, forming the base of the food web and supporting higher trophic levels. Freshwater ecosystems were highly productive areas that sustained intricate food webs. Primary producers, including algae and aquatic plants, captured sunlight and created energy through photosynthesis. Herbivorous fish and invertebrates fed on these plants, transferring energy to larger predators. Amphibians and turtles occupied multiple levels of the food chain, consuming both plants and animals. Predatory fish, crocodile-like reptiles, and other large aquatic or semi-aquatic predators maintained balance by controlling prey populations. This continuous flow of energy created interconnected communities in which every species played a part in maintaining ecological stability. Freshwater habitats were shaped not only by biological interactions but also by natural disturbances. Floods could alter river courses, deposit nutrient-rich sediments, and create temporary pools that served as breeding grounds. Droughts might shrink lakes or lagoons, concentrating organisms and increasing competition for food and space. Seasonal variations in water temperature and flow influenced reproductive cycles, migration patterns, and feeding behavior. These disturbances, though challenging, contributed to the resilience and adaptability of freshwater species, fostering diversity and promoting evolutionary innovation. The diversity of life in Jurassic freshwater ecosystems reflected a delicate balance between adaptation, competition, and environmental pressures. Fish, amphibians, and turtles evolved traits suited to specific habitats, ranging from swift river currents to still lake waters and shallow lagoons. Their interactions with plants, predators, and competitors created complex communities that were constantly changing. These ecosystems were not isolated. They connected with terrestrial and marine environments, forming a network of life that shaped landscapes and influenced evolutionary trajectories. Waterways served as lifelines, supporting life, enabling movement, and fostering the development of rich, varied ecosystems that provided the foundation for future freshwater biodiversity. The study of Jurassic freshwater ecosystems reveals patterns that continue to influence modern aquatic habitats. Rivers, lakes, and lagoons of that period were essential for the survival of numerous species, providing food, shelter, breeding grounds, and pathways for dispersal. Fish adapted to different water flows and depths. Amphibians developed complex life cycles dependent on water and land, and early turtles evolved protective shells and versatile diets. Interactions among species, coupled with environmental fluctuations, shaped the structure and function of these ecosystems. The remnants preserved in the fossil record demonstrate how freshwater habitats served as hubs of evolutionary innovation, supporting rich and dynamic communities that interacted with the broader landscapes of the Jurassic world. The intricate balance of freshwater ecosystems during the Jurassic period also relied on seasonal cycles and climatic patterns. Heavy rainfall could swell rivers, filling lakes and lagoons with nutrient-rich water that boosted productivity and provided breeding opportunities for fish, amphibians, and turtles. Dry seasons, on the other hand, could concentrate life into smaller areas, increasing competition and predation, but also facilitating dispersal and migration. This rhythm of wet and dry periods created natural pressures that shaped species behavior, life cycles, and adaptations. Some amphibians developed rapid growth or early metamorphosis to survive temporary water shortages, while fish and turtles adapted to variations in food availability and water depth. The vegetation around freshwater systems played multiple critical roles. Dense ferns, cycads, horsetails, and conifers stabilized banks and shores, preventing erosion and providing a constant supply of organic material that nourished aquatic organisms. Fallen leaves and decaying plants became food for small invertebrates, which in turn fed fish and amphibians. Submerged plants offered shelter for young fish, amphibians, and turtles, hiding them from predators and providing areas for feeding and resting. The interplay between plants and animals created microhabitats, supporting the survival and growth of numerous species, some of which left traces that are still visible in the fossil record today. Amphibians in Jurassic freshwater ecosystems displayed remarkable variety. Some were aquatic throughout their life, while others alternated between water and land. Salamander-like amphibians thrived in rivers and lakes, hunting invertebrates, algae and small fish, while larger amphibians may have preyed on smaller amphibians, insects, or fish. Reproductive strategies were diverse, with eggs laid in water developing into larvae that metamorphosed into adults, and some species taking advantage of temporary pools and slow-moving backwaters for breeding. The presence of amphibians added another layer to the food web, linking primary producers to larger predators and contributing to nutrient cycling within the freshwater habitats. Early turtles represented a unique evolutionary innovation in freshwater ecosystems. Their shells provided protection against predators, while limbs adapted for swimming allowed efficient navigation through rivers, lakes, and lagoons. Turtles could feed on aquatic plants, insects, small invertebrates, and fish, fulfilling multiple ecological roles. Some may have specialized in foraging along sediment-rich bottoms, while others focused on open water or areas with dense vegetation. Their nesting habits also influenced sediment distribution along riverbanks and lake shores, further impacting the structure of these ecosystems. Freshwater ecosystems also influenced surrounding terrestrial life. Waterways served as sources of drinking water and as hunting grounds for larger reptiles, dinosaurs, and early mammals. Riparian vegetation attracted insects and small vertebrates, which in turn drew predators. Amphibians and turtles moved between aquatic and terrestrial habitats, providing nutrients to both systems through their feeding, excretion, and mortality. Rivers, lakes, and lagoons were therefore central not only to aquatic life, but also to the broader Jurassic ecosystems, connecting land and water in ways that allowed life to flourish in a balanced and interconnected network. The fossil record preserves snapshots of these vibrant ecosystems. Fish fossils reveal a wide range of body types, feeding adaptations and behaviors. Amphibian fossils illustrate life stages from eggs to larvae to adults, as well as adaptations for both water and land. Turtle fossils show the development of shells, limb adaptations, and feeding strategies. Sediments from riverbeds, lake bottoms, and lagoon floors capture the remains of plants, invertebrates, and traces of ecological interactions. Together, these fossils provide a detailed picture of Jurassic freshwater ecosystems, showing how organisms lived, interacted, and adapted to changing environmental conditions over millions of years. The dynamic nature of Jurassic freshwater ecosystems fostered evolutionary experimentation and diversification. Fish adapted to fast currents, still waters, or shallow margins, developing features that enhanced survival and reproductive success. Amphibians experimented with life cycles and habitat use, finding ways to exploit both aquatic and terrestrial resources. Turtles evolved protective structures and versatile feeding strategies, allowing them to occupy multiple ecological niches. Seasonal changes, climatic fluctuations, and occasional environmental disturbances created pressures that encouraged resilience and adaptability, driving the evolutionary development of these freshwater species. The complex interactions within Jurassic freshwater ecosystems also created a balance that allowed multiple species to coexist. Predators regulated prey populations, herbivores controlled plant growth, and detritivores recycled nutrients. Amphibians and turtles connected aquatic and terrestrial systems, while fish served as both consumers and prey. Plant life supported food webs, stabilized sediments, and provided shelter, while water flow, depth, and chemistry influenced habitat availability. Each species contributed to the overall function of the ecosystem, maintaining productivity and diversity across rivers, lakes, and lagoons. The interplay between freshwater ecosystems and the broader Jurassic environment was intricate. Rivers carried nutrients downstream, linking highland areas to lowland lakes and lagoons. Lakes acted as reservoirs of water and life, supporting fish, amphibians, and turtles while influencing surrounding vegetation and climate. Lagoons, often isolated but nutrient-rich, served as nurseries for young fish and amphibians, supporting species that could not thrive elsewhere. Together, these habitats formed a network of freshwater ecosystems that sustained life across the Jurassic landscape, influencing evolution, biodiversity, and ecological interactions in profound ways. The adaptability of species in freshwater ecosystems contributed to long-term evolutionary trends. Fish diversified into various forms suited to different water conditions. Amphibians refined reproductive strategies to survive seasonal fluctuations and environmental pressures. Turtles developed features that allowed them to exploit multiple ecological niches and survive predation. These evolutionary innovations were crucial for the persistence of freshwater species and helped establish the ecological roles that many of their descendants continue to occupy in modern aquatic systems. Freshwater ecosystems also reflected geological and climatic processes. Sediment deposition shaped riverbeds, lake floors, and lagoon margins, creating microhabitats and influencing species distribution. Volcanic activity, tectonic shifts, and changes in sea level affected the connectivity of freshwater systems, influencing migration and dispersal patterns. Seasonal and long-term climatic changes impacted water availability, temperature, and nutrient cycles, shaping the life histories and adaptations of fish, amphibians, and turtles. These processes underscored the dynamic nature of freshwater habitats and the need for species to continually adapt to survive and thrive. The behavior of aquatic and semi-aquatic species in Jurassic freshwater ecosystems was shaped by predation, competition, and environmental conditions. Fish evolved schooling behaviors to avoid predators, specialized feeding techniques to exploit available resources, and reproductive strategies to ensure the survival of offspring. Amphibians displayed complex breeding behaviors and life cycle adaptations, while turtles navigated both water and land to feed, reproduce, and avoid threats. These behaviors not only allowed species to survive in specific habitats, but also influenced the structure and function of the ecosystems in which they lived, maintaining ecological balance and fostering biodiversity. Over 230 million years ago, during a time known as the Late Triassic period, the very first true dinosaurs began to appear on Earth. These early dinosaurs were small, mostly bipedal creatures that moved with agility and hunted or foraged to survive in a world that was dominated by other large reptiles, amphibians, and a variety of strange, now extinct creatures. The earliest dinosaurs were not the giant, awe-inspiring animals that would later capture the imagination of people in stories and museums. Instead, they were modest in size, often only reaching a few feet in length, and they had long, slender legs, sharp teeth, and nimble tails that helped them balance while running. Some of these early dinosaurs were meat-eaters, known as theropods, which walked on two legs and had sharp claws and teeth for catching small prey, while others were plant-eaters, called sauropodomorphs, which were beginning to explore the idea of feeding on the plentiful ferns, cycads, and conifers that covered the Earth's surface. As the Triassic period gave way to the Jurassic period, around 199 million years ago, the world started to change in ways that allowed dinosaurs to grow larger and more diverse. Continents were still slowly drifting apart from the supercontinent called Pangaea, forming long coastlines, shallow seas, and vast inland regions. The climate was generally warm and humid, with occasional dry seasons that created environments ranging from dense forests to open plains. These changes in climate and geography created new opportunities for dinosaurs to evolve into a wider range of forms. Small early dinosaurs gave rise to much larger relatives, and the first giant herbivores began to appear. These large plant-eating dinosaurs, known as sauropods, developed long necks and tails, enormous bodies, and thick, pillar-like legs that allowed them to reach the tallest trees and move slowly across the land in search of food. Their massive size made them almost untouchable for most predators of the time, although theropods were beginning to adapt to hunting larger prey as well. By the early Jurassic period, about 193 million years ago, dinosaurs were becoming the dominant land animals in many regions. The plant-eating sauropods, such as early relatives of the well-known Brachiosaurus and Diplodocus, were developing the characteristics that would later define the largest land animals the planet had ever seen. Their necks grew longer and stronger, sometimes reaching lengths of over 40 feet, allowing them to browse from the tops of towering conifers and cycads. Their tails became powerful tools, used for balance, communication, and perhaps even defense against attacking predators. Sauropods began to travel in herds, a behavior that may have helped protect the younger and weaker members from carnivorous dinosaurs. Their sheer size meant that even the largest carnivores had to approach carefully, making the herbivores almost invincible except to the most determined hunters. During the same period, theropod predators were also evolving rapidly. These carnivorous dinosaurs range from small, swift hunters to larger, more fearsome species capable of preying on adult sauropods. Early Jurassic theropods, like Dilophosaurus, measured around 20 to 25 feet in length and had distinctive crests on their heads, perhaps used for display or attracting mates. These predators developed powerful hind legs, sharp claws, and serrated teeth, all specialized for catching and killing other animals. As the Jurassic progressed, theropods became more sophisticated hunters, developing keen senses of sight and smell, complex social behaviors, and strategies for hunting in groups or ambushing prey. The evolutionary arms race between predators and herbivores drove many adaptations, leading to the rise of enormous sauropods and increasingly agile and intelligent theropods. By the Middle Jurassic period, roughly 165 million years ago, dinosaurs had spread to nearly every corner of the planet. Vast forests of conifers, cycads, and ferns provided abundant food for herbivores, while the oceans teemed with fish, cephalopods, and other marine life that influenced the diet of coastal or riverine dinosaurs. Herbivorous dinosaurs diversified into several groups, each with unique adaptations. The stegosaurs, for example, developed rows of bony plates along their backs and spikes on their tails, possibly for defense and display. Their brains were small compared to their bodies, but their physical adaptations helped them survive in environments filled with large predators. Meanwhile, ornithopods, another group of herbivores, developed beaks and specialized teeth for efficiently eating tough vegetation, as well as strong hind legs for running and avoiding predators. The evolution of such varied herbivorous forms allowed different species to occupy specific niches, reducing direct competition for the same food sources and supporting a rich and balanced ecosystem. Predatory dinosaurs also continued to diversify in the Middle Jurassic. Large theropods like Megalosaurus and later Allosaurus grew to lengths exceeding 30 feet, with powerful jaws and limbs capable of bringing down even the largest sauropods. These predators were among the apex hunters of their time, and their evolutionary success pushed herbivores to develop even more extreme adaptations. Some sauropods developed longer necks and reinforced vertebrae, while others evolved enormous tails that could swing with devastating force to deter attackers. Predators experimented with new hunting techniques, including stalking, ambush, and cooperative hunting, although direct evidence of pack hunting remains debated among scientists. As the Jurassic period progressed toward its later stages, around 150 million years ago, dinosaur diversity reached new heights. Sauropods continued to evolve into massive forms like Brachiosaurus, Diplodocus, and Apatosaurus, reaching lengths of 70 to 100 feet and weights exceeding 50 tons. These enormous animals roamed in herds across vast plains and forested regions, leaving behind trails of footprints that would be preserved for millions of years, providing crucial evidence for modern paleontologists. Their long necks allowed them to reach food unavailable to other herbivores, and their social behavior may have included complex interactions such as group movement, coordinated feeding, and protection of young. At the same time, stegosaurs like Stegosaurus, with their plated backs and spiked tails, defended themselves effectively against predators, demonstrating that herbivores could also evolve impressive means of survival beyond size alone. Theropod predators during the late Jurassic also achieved remarkable sizes and adaptations. Allosaurus, for instance, reached lengths of up to 35 feet, with strong muscular bodies and large serrated teeth capable of slicing through flesh. Their skulls were light but reinforced with struts to withstand the forces of biting, and their sharp claws on the hands and feet enhanced their ability to capture struggling prey. Some theropods began to exhibit more sophisticated hunting behaviors, possibly including ambush tactics or cooperative strategies when attacking larger herbivores. This period marked an ongoing evolutionary battle between predator and prey, where each adaptation in one group could provoke a counter-adaptation in the other, driving the development of specialized features such as longer necks, reinforced armor, and increasingly powerful hunting tools. Throughout the Jurassic, other herbivorous dinosaurs developed distinct strategies for survival. Ornithopods, for example, continued to evolve beaks and rows of teeth suitable for grinding and slicing tough plant material, often travelling in herds to provide safety in numbers. Small herbivorous dinosaurs, including early relatives of later duck-billed species, began exploring new niches, feeding on low-lying plants or foraging in areas less accessible to giant sauropods. These smaller herbivores may have relied on speed and agility rather than size for protection, demonstrating the wide variety of survival strategies that evolved in response to predation pressures. Additionally, stegosaurs and ankylosaurs developed armor and defensive weapons, such as plates, spikes, and club-like tails, illustrating that defensive adaptations could be as effective as sheer size in deterring predators. The evolution of dinosaur reproduction also played a role in their diversification. Fossil evidence from the Jurassic shows that many dinosaurs laid eggs in nests, sometimes in communal nesting grounds, and cared for their young in ways that increased survival rates. Some theropods may have guarded their nests or young, while sauropods likely relied on numbers and herd protection to keep hatchlings safe. The strategies employed by different species influenced population growth and survival, enabling certain lineages to flourish, while others declined or became extinct. Over time, these reproductive strategies contributed to the wide array of dinosaur forms that spread across the continents. By the end of the Jurassic period, approximately 145 million years ago, dinosaurs had become the dominant land animals across nearly all habitats, from lush forests and floodplains to arid regions and river valleys. Herbivorous dinosaurs had achieved sizes and specializations that allowed them to exploit nearly every type of vegetation available, while theropods had developed into some of the most efficient and powerful predators Earth had ever seen. The diversity of forms, behaviours, and adaptations among both herbivores and carnivores during the Jurassic set the stage for further evolution in the Cretaceous period, where even more incredible giants and cunning hunters would emerge. The fossil record from this period, preserved in regions that today include parts of North America, Europe, Africa, and Asia, reveals astonishing variety. Sauropod skeletons with their elongated vertebrae and massive limbs are found alongside the remains of stegosaurs with their armoured plates and theropods with sharp claws and teeth. These fossils provide insight into the evolutionary experimentation that occurred over millions of years as dinosaurs adapted to changing climates, shifting continents, and the constant pressures of predation and competition. The physical diversity alone, from the towering Brachiosaurus stretching high into the trees to the heavily armoured Stegosaurus and the swift-hunting Allosaurus, demonstrates the remarkable evolutionary success of these creatures during the Jurassic. Even within single groups of dinosaurs, variation was immense. Sauropods like Diplodocus had whip-like tails that could reach lengths of 40 to 50 feet, and may have been used for defence, while Brachiosaurus developed forelimbs longer than their hind limbs, giving them a high browsing advantage in tall forests. Theropods such as Ceratosaurus had large nasal horns, possibly used in displays or combat, illustrating that even predators developed distinctive traits beyond hunting efficiency. Stegosaurs, with their alternating rows of plates, may have used these structures to regulate body temperature or communicate, showing that adaptation was not only functional, but also social and ecological. The interplay between herbivorous and carnivorous dinosaurs drove much of the evolutionary innovations seen during the Jurassic. The enormous size of sauropods challenged predators to become more efficient hunters, while the development of armour and defensive structures among herbivores forced predators to adapt new strategies. Speed, intelligence, cooperative hunting, and physical adaptations were all tested against the defensive measures and sheer mass of herbivores, creating a dynamic evolutionary environment where survival depended on constant innovation. Dinosaurs also evolved alongside other animals and plants in the Jurassic world. The abundance of ferns, cycads, conifers, and the earliest flowering plants provided diverse food sources, while freshwater ecosystems supported fish, amphibians, and early reptiles that sometimes formed part of the diet of smaller theropods. Predators adapted to various prey types, hunting in forests, along rivers, and across open plains. Meanwhile, herbivores developed adaptations to feed efficiently, digest tough plant material, and avoid predation. These interactions created complex ecosystems where dinosaurs occupied multiple levels of the food chain, from small herbivores hiding among ferns to giant sauropods grazing among treetops and apex predators patrolling the land. The rise of dinosaurs during the Jurassic period represents one of the most significant evolutionary success stories in Earth's history. Over tens of millions of years, small, unremarkable early dinosaurs evolved into an astonishing variety of forms, from massive, long-necked giants to swift, deadly hunters and heavily armoured herbivores. Each adaptation, from physical size and defensive structures to hunting strategies and reproductive behaviours, contributed to the flourishing of dinosaurs across the continents. Their diversification created landscapes teeming with life, where forests, plains, rivers and coastal areas all hosted different species interacting in a complex web of survival and adaptation. Fossils from this time, including bones, teeth, tracks, and even preserved nests and eggs, continue to reveal the story of dinosaur evolution. They show that herbivores were not only large and powerful, but also highly varied in their feeding strategies and physical defenses, while predators range from small, opportunistic hunters to massive, highly specialized carnivores. The evidence of social behavior, group movement, and possibly even communication among dinosaurs adds another layer to our understanding of their evolution. These discoveries emphasize that the rise and diversification of dinosaurs were not random, but shaped by millions of years of ecological pressures, competition, and adaptation. By the late Jurassic, dinosaurs had established ecological dominance that would last for tens of millions of years. Sauropods like Brachiosaurus and Diplodocus shaped the vegetation and landscapes around them, while stegosaurs and ornithopods maintained balance in the herbivore communities. Theropods such as Allosaurus and Ceratosaurus enforced the rule of predator and prey, ensuring that no species could dominate without facing evolutionary consequences. The interplay of growth, defense, speed, intelligence, and social behavior created a vibrant, dynamic world where dinosaurs continually evolved, diversified, and thrived. Every fossil discovered from the Jurassic period is a testament to the long and intricate process of evolution that led from small, nimble ancestors to some of the most impressive land animals ever to walk the Earth. Each bone, footprint, and fossilized egg provides clues about their anatomy, behavior, and interactions, painting a vivid picture of life over 145 million years ago. The rise of herbivores with massive bodies, specialized feeding structures, and protective adaptations, alongside the evolution of predators with keen senses, powerful limbs, and hunting strategies, illustrates a remarkable story of survival, adaptation, and diversification that shaped the world in ways still visible in the fossil record today. The dinosaur ecosystems of the Jurassic were complex, full of interdependencies, and subject to constant change. The diversification of large herbivores influenced predator evolution, while predators shaped herbivore behavior, size, and physical defenses. Vegetation, climate, geography, and other animals all played critical roles in guiding the evolutionary path of dinosaurs. The fossil evidence demonstrates that from small beginnings in the late Triassic, dinosaurs expanded into a wide range of forms and sizes, adapted to many different habitats, and dominated terrestrial ecosystems for tens of millions of years. Even within individual species, adaptations were remarkable. Some sauropods developed specialized teeth to strip leaves efficiently, while others had long necks to reach tall conifers. Some stegosaurs used tail spikes as defensive weapons, and ornithopods evolved strong jaws and teeth for grinding tough vegetation. Theropods continued to refine hunting techniques, with some species adapting for speed, stealth, or cooperation. Each adaptation added to the overall diversity, allowing multiple species to coexist and fill ecological niches across forests, floodplains, plains, and river valleys. The fossil evidence from North America, Europe, Africa, and Asia shows that dinosaurs were not only physically diverse, but also behaviorally complex. Herding, nest guarding, and possible social communication suggest that even millions of years ago, dinosaurs had developed intricate behaviors to enhance survival. These behaviors, combined with physical adaptations and ecological pressures, contributed to the astonishing diversification seen during the Jurassic period. The evolutionary success of dinosaurs set the stage for continued innovation, specialization, and dominance in the Cretaceous period, building on the foundations laid over tens of millions of years of Jurassic evolution. Every step in the evolution of herbivores and predators during the Jurassic was shaped by survival pressures, competition for food, predator-prey dynamics, and environmental changes. Large herbivores became the dominant consumers of vegetation, while predators adapted to overcome their defenses. Social behaviors, physical adaptations, and ecological interactions all contributed to the rich diversity of dinosaur life. Fossils, tracks, and eggs provide evidence of these adaptations, showing how dinosaurs grew from small, early forms to massive, specialized creatures that defined the terrestrial ecosystems of the Jurassic world. The rise and diversification of large herbivores and predators during the Jurassic period is evident in the fossil record, illustrating an era of dramatic evolutionary change. Herbivores evolved size, defense, and specialized feeding strategies, while predators developed speed, intelligence, and powerful hunting tools. These evolutionary innovations allowed dinosaurs to occupy nearly every habitat and ecological niche, creating ecosystems that were both complex and dynamic. The interplay between herbivores, predators, and the environment drove continual adaptation, resulting in a remarkable diversity of forms and behaviors that dominated the land for millions of years. Herbivorous dinosaurs continued to expand in size and specialization. Sauropods reached lengths exceeding 100 feet, with necks that allowed them to access high foliage and tails that provided balance and defense. Ornithopods evolved efficient teeth for processing vegetation, and stegosaurs displayed defensive plates and spiked tails. These adaptations allowed herbivores to thrive in a variety of environments, from dense forests to open plains, while also influencing predator evolution. Theropod predators evolved alongside their herbivorous counterparts. Large species like Allosaurus developed powerful jaws and sharp teeth, capable of hunting enormous sauropods, while smaller theropods refined speed, stealth, and intelligence. Predatory adaptations were driven by the need to overcome the defenses of herbivores, resulting in an ongoing evolutionary struggle that shaped the physical and behavioral traits of both groups. The fossil evidence from the Jurassic world demonstrates the extraordinary success of dinosaurs during this time. Skeletons, footprints, eggs, and nest sites reveal a world in which large herbivores and predators coexisted in complex ecosystems. The interactions between different species, combined with environmental pressures and adaptations, fueled the diversification of dinosaurs, leading to the rise of some of the largest and most specialized land animals in Earth's history. In conclusion, the Jurassic period was a time of incredible evolutionary experimentation and diversification for dinosaurs. Large herbivores developed size, defense, and specialized feeding adaptations, while predators evolved to meet these challenges with power, speed, and cunning. The fossil record provides vivid evidence of these changes, showing a world where dinosaurs were the dominant terrestrial animals, continually evolving, diversifying, and shaping the landscapes around them. The rise and diversification of these remarkable creatures during the Jurassic laid the groundwork for continued evolutionary success in the millions of years that followed. The ecosystems created by herbivorous and carnivorous dinosaurs were complex and dynamic. Large herbivores influenced vegetation patterns and landscape use, while predators shaped prey behavior and population dynamics. These interactions drove ongoing adaptations in anatomy, behavior, and social organization, resulting in a rich and diverse array of dinosaur species. Fossil evidence reveals that dinosaurs were highly successful in adapting to changing environments, demonstrating an extraordinary ability to evolve and thrive over tens of millions of years. The rise and diversification of dinosaurs during the Jurassic period is one of the most remarkable chapters in Earth's evolutionary history. Herbivores became giants, predators became efficient hunters, and together they formed complex ecosystems that dominated terrestrial life. Fossil evidence, including bones, tracks, eggs, and nests, shows the physical and behavioral adaptations that allowed these creatures to flourish. The interactions between herbivores, predators, and their environment drove continual evolution, resulting in a rich and varied dinosaur fauna that shaped the landscapes of the Jurassic world and left an enduring legacy in the fossil record. The Jurassic period, spanning from 199 million to 145 million years ago, witnessed the remarkable rise and diversification of dinosaurs. Small, early forms evolved into massive herbivores with long necks, powerful limbs, and specialized teeth and jaws designed to process vast amounts of plant material efficiently. Sauropods such as Brachiosaurus, Diplodocus, and Apatosaurus became true giants, with some individuals exceeding 70 to 100 feet in length and weighing tens of tons. Their sheer size not only allowed them to reach vegetation unavailable to smaller herbivores, but also provided a form of passive defense against predators. The evolution of extremely long necks and tails, massive bodies and robust limb structures allowed these herbivores to exploit resources in ways that no other land animals could. Their large, barrel-shaped bodies contained enormous digestive systems capable of processing fibrous plants such as cycads, conifers and ferns, while their teeth and jaw structures were often adapted to stripping leaves rather than chewing extensively, allowing for continuous feeding over many hours each day. Smaller herbivorous dinosaurs such as the ornithopods also flourished during the Jurassic. These animals developed specialized teeth and jaws for grinding and slicing vegetation, allowing them to feed on a wide variety of plant material. Many ornithopods were fast and agile, enabling them to escape from predators rather than rely solely on size or armor for protection. Herding behavior, inferred from fossilized trackways and nesting sites, may have provided additional safety and facilitated social interactions that improved survival. These behaviors illustrate the diversity of strategies that herbivorous dinosaurs developed to thrive in different environments, from dense forests to open plains and along river valleys. Stegosaurs, a group of herbivorous dinosaurs that became widespread in the Middle to Late Jurassic, displayed unique adaptations that combined defense and display. Their bony plates, which ran along their backs in alternating rows, may have been used to regulate body temperature, communicate with other individuals, or intimidate predators. Their tails were equipped with large spikes, sometimes referred to as thagomizers, which could be swung with great force to deter attackers. Despite having relatively small brains, stegosaurs survived effectively in the predator-rich Jurassic environment, relying on physical defenses, herd behavior, and possibly social interactions to maintain their populations. The presence of these specialized herbivores demonstrates the inventive ways in which different dinosaur lineages adapted to survival pressures. Theropod predators continued to evolve alongside herbivorous dinosaurs, increasing in both size and specialization. Early Jurassic theropods such as Dilophosaurus were medium-sized predators, roughly 20 to 25 feet long, equipped with sharp teeth and claws that allowed them to capture small to medium-sized prey. By the Middle and Late Jurassic, larger theropods like Allosaurus and Ceratosaurus emerged, growing to lengths exceeding 35 feet. These apex predators had muscular bodies, strong jaws, and serrated teeth capable of slicing through flesh and bone, allowing them to hunt large herbivorous dinosaurs. Some theropods may have engaged in complex hunting strategies, including ambush tactics or cooperative hunting, which required a level of social interaction and intelligence that continues to fascinate scientists today.